Did you know that China built a dam so massive it changed the way Earth rotates? But now they are building a hydrostation 3 times bigger, from 1,000-mile tunnels below water to megatall skyscrapers going into the sky, and from changing river pathways to mega bridges twice as tall as the Eiffel Tower. We are bringing you 29 of China's biggest mega projects ever. Don't miss out as we bring the story of how China is turning these insane ideas into reality. Starting with number 29. When you concentrate 39 billion cubic meters of water at a higher elevation than it would naturally sit, you change Earth's moment of inertia. The planet's rotation slows down, not by much, just 0.06 microseconds per day, but enough for the scientists to measure it. That's the scale we're dealing with when we talk about the Three Gorges Dam. China needs such an extreme dam to deal with. The Yangtze River, the longest river in Asia, which regularly flooded with devastating consequences. For centuries, these floods killed thousands, destroyed crops, and wiped out entire communities. At the same time, China's explosive economic growth demanded massive amounts of electricity. Coal plants were choking cities with pollution. The country needed clean energy and flood control, and they needed it at a scale that matched their population of over 1 billion people. The solution was to build the world's largest hydroelectric dam right in the middle of the Yangtze, a dam that would create a reservoir 600 kilometers long, stretching back through some of China's most iconic landscapes. Construction began in 1994 on the Yangtze River, and from the first day, nothing about this project was ordinary. The dam wall stretches 2.3 kilometers across the river valley and rises 181 meters, roughly the height of a 60-story building. But calling it a building doesn't capture the sheer mass of the thing. They poured 28 million cubic meters of concrete, 16 times more than the Hoover Dam. At peak construction, 26,000 workers were on site around the clock, essentially building a small city out of concrete that had to be strong enough to hold back a reservoir containing 39 trillion kilograms of water. Think about what that means for the construction process. You can't just pour concrete in a solid mass. The chemical reaction that makes concrete harden generates enormous heat. In a structure this large, if you pour too quickly, the interior heats up while the exterior cools, creating temperature differentials that cause the concrete to crack and fail. Engineers had to pour in carefully planned layers, allowing each section to cool before adding the next. The concrete mix itself was specially formulated to generate less heat during curing. Even with these precautions, cooling pipes were embedded throughout the structure, circulating chilled water to control temperatures during the years-long curing process. But the dam is only part of the story. The Yangtze is China's main inland waterway, carrying cargo vessels that keep the country's interior economy running. Block the river with a dam, and you've just created an economic catastrophe. So they built the world's largest ship locks, 2 parallel systems of chambers that lift vessels 113 meters, the equivalent of a 30-story building. Each lock chamber is 280 meters long and 35 meters wide. Ships enter the lower chamber, massive gates close behind them, and millions of gallons of water flow in, lifting the vessel to the next level. It takes about 4 hours for a ship to transit from the lower Yangtze to the reservoir behind the dam. The power generation is what really sets this apart. 32 turbines, each one generating 700 megawatts, are housed in the dam. Combined output, 22,500 megawatts, roughly equivalent to 15 large nuclear power plants. In a good year, the dam generates over 100 billion kilowatt hours of electricity. That's enough to power multiple provinces. That clean hydroelectric power replaces coal plants that would have pumped millions of tons of CO2 into the atmosphere annually. But you can't build something this massive without consequences that ripple outward in every direction. Over 1.3 million people were relocated to make way for the reservoir. Entire cities, some with histories stretching back thousands of years, were submerged. Ancient temples disappeared underwater. Communities that had existed in the same location for generations were forced to move to new, often hastily constructed resettlement towns. The government called it necessary progress and paid compensation. For many who lost their homes and ancestral lands, no amount of money made it right. The environmental impact continues to generate debate. The The reservoir traps sediment that the Yangtze would naturally carry downstream. That sediment used to nourish farmland and ecosystems along the river and in the delta. Without it, erosion patterns have changed. Farmland productivity has declined in some areas, and the coastline is actually retreating in places. Fish populations crashed when their migration routes were blocked. The Chinese river dolphin, already endangered, may have been pushed to extinction, partly because the dam fragmented its habitat beyond recovery. Landslides around the reservoir have become more frequent. As water levels fluctuate seasonally, the ground along steep valley walls becomes saturated and then dries out, destabilizing slopes that were stable for millennia. Some landslides have been large enough to create tsunami-like waves in the reservoir, threatening communities along the shore. Yet the dam has also prevented catastrophic flooding. In 2010 and 2012, floods that would have killed thousands and caused tens of billions in damage downstream were controlled by the reservoir's storage capacity. The dam's operators can hold back water during peak floods and release it gradually, protecting cities that would otherwise be inundated. This flood control benefit alone, supporters argue, justifies the project. The dam opened for power generation in 2003, with the final turbines coming online in 2012. The official cost was approximately $37 billion, but that doesn't account for relocation expenses, environmental mitigation efforts, or the lost cultural heritage now buried underwater. The true cost, economic and otherwise, is still being calculated decades later. Today, the Three Gorges Dam stands as both triumph and tragedy, a monument to human capability that produces clean energy for hundreds of millions of people, while serving as a reminder that megaprojects of this scale always extract a price. Next, we have yet another dam, which might not be as big, but the difficulty of construction makes it equally impressive. We begin with a Shanghai landmark and a financial icon, soaring up to a height of 632 meters into the sky. The workers called it the Dragon, as the building rose floor by floor above Shanghai's Lujiazui financial district. Its twisted shape looked like a dragon spiraling into the sky. By the time they finished in 2015, they had built something that would dominate China's skyline for years to come. It is the third tallest building in the world, surpassed only by the Burj Khalifa in Dubai and the Merdeka 118 in Malaysia. But here's the interesting part. Shanghai Tower's highest usable floor sits at 587 meters, which actually beats the Burj Khalifa's top floor at 584 meters. In practical terms, this makes it the tallest building where people can actually work and live. Construction began in November 2008, contracted by Shanghai Construction Group. The project cost $2.4 billion, which sounds massive until you compare it to similar buildings in New York. One World Trade Center cost nearly $4 billion for roughly the same height. Chinese construction costs run about half of what American developers pay, partly because labor costs in China average around $3.36 per hour compared to over $17 in New York. The design came from American architectural firm Gensler. They created something that had never been attempted at this scale before, a building that twists 120 degrees as it rises. The shape isn't just for show. That twist reduces wind load on the building by 24%. In practical terms, this meant engineers could use 25% less structural steel than a conventional straight-sided tower of the same height. The savings added up to $58 million in materials alone. The Shanghai Tower is actually 9 separate cylindrical buildings stacked on top of each other. Each cylinder contains 12 to 15 floors, and together they form distinct zones with their own atriums, gardens, cafes, and retail spaces. The building's double-layered glass facade wraps around all 9 zones, with the space between the inner and outer glass layers acting as a climate buffer. This double-skin design serves a specific purpose. In winter, the airspace between the glass layers warms up cold outside air before it enters the building. In summer, heat from inside dissipates in the buffer zone before it can stress the air conditioning. The result, the building uses 21% less energy than a comparable conventional tower. Wind turbines built into the facade and near the top generate 350,000 kilowatt-hours of supplementary electricity per year, about 10% of the tower's needs. The construction process itself was a masterpiece of coordination. Workers used a repetitive slip-forming process to build the core floor by floor. By April 2011, steel reinforcement had reached the 18th floor while the concrete core stood at the 15th floor. The pace accelerated through 2012 and 2013. By the end of 2012, the tower had reached the 91st floor and stood approximately 425 meters tall. The moment everyone had been waiting for came on April 11, 2013, when the tower passed 500 meters and surpassed both of its neighboring super-talls, the Jinmao Tower and the Shanghai World Financial Center. On August 3, 2013, construction crews laid the final structural beam at the top, officially topping out China's tallest building. At the ceremony, Gensler co-founder Art Gensler declared, "Shanghai Tower represents a new way of defining and creating cities." The elevator system required its own technological breakthrough. Mitsubishi Electric designed elevators that travel at 20.5 meters per second, that's 74 kilometers per hour, faster than the speed limit on most city streets. These are the fastest elevators in the world. They can carry passengers from ground level to the 118th floor in just 55 seconds. 3 of these ultra-high-speed elevators serve the observation deck, supplemented by 3 firefighter elevators that increase throughput during peak hours. Shanghai Tower's observation deck is the highest in the world. Located on the 121st floor at 561 meters, it opened in 2020 under the name Top of Shanghai. This beat the previous record holder, the observation deck on the Burj Khalifa at 555 meters. Visitors standing on this deck can see the entire sprawl of Shanghai laid out beneath them, the winding Huangpu River, the colonial architecture of the Bund, and the forest of towers in Lujiang. But the tower's success story isn't simple. For several years after completion, large sections of the upper floors remained empty. The double-skin design that makes the building so energy efficient also reduces usable floor space by about 50% compared to a conventional building. The triangular floor plate, while beautiful and aerodynamically optimal, creates irregular office spaces that some tenants found difficult to use. Financial losses mounted as premium floors sat vacant month after month. Critics called the Shanghai Tower a white elephant, a monument to ambition that didn't make economic sense. Marshall Strabala, chief architect at Gensler, pushed back hard against these claims. "I would say that the person who said that doesn't know what they're talking about." By 2021, occupancy began climbing as the J Hotel opened and boutique office spaces in the upper floors found tenants. The building's unique amenities, the observation deck, the art space on floors 125 to 126, the Duoyun Books bookstore with free entry and observation decks, started drawing visitors in numbers that justified the investment. The Shanghai Tower also serves as a symbol of China's environmental commitments. The building earned praise as the greenest super high-rise building on Earth. The skyscraper is part of the city's super high-rise precinct on the Huangpu River opposite downtown Shanghai. Its neighbors include the 421-meter-high Jinmao Tower and the 492-meter-high Shanghai World Financial Center by Kohn Pedersen Fox. However, none of those buildings come close to the next entry on our list. Start with a bridge whose deck floats 625 meters above the river below. A bridge built at heights so extreme that construction workers needed to undergo psychological evaluation before they were allowed on site. It's taller than China's tallest building, the Shanghai Tower, and equivalent to stacking 2 Eiffel Towers end to end. The deck is so high that if you dropped a rock from the top, it would fall for approximately 11 seconds before hitting the water. Built in southwestern China over the Baihetan River, Huajiang Canyon Bridge is now the highest bridge in the world. The bridge is also set to become the longest spanning mountain bridge in the world, with a total length of 2,890 meters. The Huajiang Canyon Bridge employs a cable-stayed design where the deck hangs from cables connected to tall towers. Unlike suspension bridges where cables drape between towers and the deck hangs from vertical suspenders, cable-stayed bridges use cables that run diagonally from the towers directly to the deck, creating a distinctive fan or harp-like appearance. This design offers several advantages for the extreme conditions at Huajiang. Cable-stayed bridges are more rigid than suspension bridges, making them better at handling the constant traffic loads while resisting wind-induced movement. They're also more efficient for medium-length spans, like Huajiang Bridge's 1,000-meter main span. The towers themselves rise approximately 300 meters above the deck, meaning the absolute highest points of the bridge structure soar nearly 925 meters above the river, taller than the tallest building in most cities, perched on the edge of a mountain plateau. The construction timeline for the Huajiang Canyon Bridge began in 2019, with completion scheduled for 2025, representing a 6-year marathon of engineering precision in one of the most hostile construction environments imaginable. However, turning the idea of such an extreme bridge into reality was not easy. Building at these heights introduces challenges that don't exist for normal bridges. The first problem is wind. At 625 meters above a river valley, wind speeds can exceed 200 kilometers per hour during storms. The bridge had to be designed to handle not just the pressure of wind pushing against its surface, but also the complex aerodynamic effects that can cause catastrophic oscillations. Engineers conducted extensive wind tunnel testing using scale models of the bridge, subjecting them to simulated typhoons and mountain wind patterns. To counter these winds, workers had to anchor the bridge towers deep into the mountainside to handle the enormous forces from the suspended deck. The second challenge was getting materials to the construction site. The bridge location is so remote and the terrain so hostile that conventional construction equipment couldn't reach it. Engineers had to build temporary access roads carved into cliff faces, sometimes with clearances so tight that trucks could only pass within centimeters of the edge. Some equipment had to be airlifted by helicopter, adding millions to the construction budget. Despite its apparent grandeur, the bridge has a much more practical purpose. Before this bridge, communities on opposite sides of the canyon were separated by a journey that could take half a day through winding mountain roads. Once completed, the Huajiang Canyon Bridge will reduce this to less than 3 minutes. The bridge is part of the Pu'an to Panzhou Expressway, connecting multiple provinces across southwestern China. For approximately 300,000 people living in the surrounding counties, this means agricultural products can reach urban markets faster, students can access better schools, and medical facilities become available to the entire region. It's because of these far-reaching economic benefits that China has invested $500 million into the project. Despite the construction challenges, China's Guizhou province has become the unexpected capital of high-altitude bridge engineering. The province is home to dozens of the world's 100 highest bridges, transforming what was once a barrier into a testing ground for China's bridge engineering capabilities. But this recently opened structure isn't the only behemoth in the province. In fact, the Huajiang Canyon Bridge took the title of the highest bridge in the world from another soaring structure just 200 kilometers away. It is the Baihetan Bridge, also known as the Duge Bridge, which lies 565 meters above the water and was just as complex to build. Imagine trying to build a railway to the roof of the world. That's exactly what's happening across the Tibetan Plateau right now, where trains will soon be racing at 250 kilometers per hour through terrain where most people need oxygen tanks just to walk. And if you think that sounds difficult, you haven't heard the half of it. Tibet sits on a plateau averaging 4,500 meters above sea level. That's higher than most commercial aircraft fly when they're cruising. Construction workers can't swing a hammer for more than a few minutes without gasping for breath. Concrete takes twice as long to set, and diesel engines lose nearly half their power. And then there's the ground itself. Much of the route crosses permafrost, ground that's been frozen solid for thousands of years. You might think frozen ground would be stable, perfect for building on. Except when you put a railway on top of it, the ground starts to warm up. The permafrost melts. What was once solid earth turns into unstable mud that can swallow entire sections of track. Engineers watched test sections sink meters into the ground within months. The solution they came up with reads like science fiction. They're building the railway on thousands of elevated bridges, but these aren't ordinary bridges. Inside the support pillars, liquid ammonia circulates through a network of pipes, acting like a massive refrigeration system. The ammonia absorbs heat from the ground, keeping the permafrost frozen even as 200-ton trains thunder overhead at high speed. Each pillar is essentially a giant freezer, working 24/7 to fight against the natural warming effect of the railway itself. At these altitudes, diesel locomotives lose so much power they can barely pull their own weight, let alone a full passenger train. China developed specialized locomotives with turbocharged engines that force extra air into the combustion chambers, compensating for the thin atmosphere. Even with this technology, the trains need more powerful engines than equivalent railways at sea level. Then there's the human factor. Passengers traveling at these altitudes for hours would experience severe altitude sickness. Maintaining an artificial atmosphere equivalent to 2,800 meters, even when the train is traveling at 4,500 meters. Oxygen is pumped into the cars continuously. Medical staff ride on every train. Emergency oxygen masks are built into every seat. The construction logistics alone are staggering. When something breaks, and at this scale, something always breaks, the nearest city with adequate supplies might be 1,000 kilometers away. Workers couldn't just order materials and expect delivery in a few days. They had to build entire temporary cities on the plateau, complete with concrete factories, steel fabrication plants, power generation facilities, and housing for over 100,000 workers. These camps operate in temperature swings from 30 degrees Celsius during the day to -20 at night. The existing Shanghai-Tibet Railway, completed in 2006, was already considered an engineering marvel, but that line tops out at 160 kilometers per hour. The new extensions push speeds up to 250 kilometers per hour through even more challenging terrain. Routes to Ningxi snake through valleys where the Indian and Eurasian tectonic plates are actively colliding, pushing the Himalayas upward by about 5 millimeters every year. The track beds are designed with flexible joints that can handle the ground shifting during earthquakes without derailing trains. Some sections required drilling tunnels through mountains at elevations where even the tunnel boring machines had to be specially modified to operate. The air inside the tunnels during construction was so thin that diesel equipment wouldn't run properly. They had to use electric machinery powered by generators, creating a whole additional layer of complexity. Different segments are at different stages of completion. Some sections are already operational, cutting travel times dramatically. Other sections are still in active construction, blasting through mountains, spanning impossible gorges with bridges that seem to hang in mid-air, laying tracks across permafrost that constantly threatens to undermine the whole enterprise. Full completion of the entire network won't happen until the 2030s. And even that timeline assumes no major setbacks. When finished, this will be the highest railway network on Earth, operating in conditions that would shut down virtually any other transportation system. Travel times from Beijing to Lhasa will drop from over 40 hours to potentially under 15. Tourism, development, and economic integration will accelerate. But there's a cost beyond the engineering challenges. Critics point out that easier access accelerates cultural change in one of the world's most unique regions. Environmental groups worry about the impact on fragile, high-altitude ecosystems, and there's no ignoring the strategic angle. A high-speed railway to Tibet makes it much easier to move military resources to sensitive border regions. When it's done, it will be the highest railway on Earth, operating in conditions that would shut down virtually any other transportation system on the planet. It's engineering at the absolute edge of what's possible. But as impressive as building a railway to the sky sounds, we are only beginning. Because what comes next harnesses more raw power than almost anything humanity has ever built and literally changed how fast the Earth spins. In September 2015, construction workers in Tianjin topped out a skyscraper that would have become China's tallest building. At 597 meters and 128 floors, Goldin Finance 117 beat Shanghai Tower to completion by several months. Then, everything stopped. The concrete stood. The steel frame reached its full height. But in December 2015, workers packed up and left. The building has stood empty ever since, making it the world's tallest unoccupied building according to Guinness World Records. But how did that happen? Goldin Properties, the Hong Kong-based developer, started construction in 2008 with big ambitions. The company planned Goldin Finance 117 as the centerpiece of an entire district called Goldin Metropolitan. The vision included luxury residences, entertainment venues, 2 international polo fields, retail spaces, and green areas spread across almost 2 square kilometers of land in Tianjin's new business district. The tower itself was designed to look like a walking stick topped with a diamond. The upper floors would house a 5-star hotel. The middle sections contained office space. A diamond-shaped atrium at the top included a swimming pool and observation deck. The design came from P&T Group, with structural engineering by Arup, the London firm famous for solving impossible engineering problems. And the engineering was truly challenging. The tower stands at a height-to-width ratio of 9.5 to 1, which exceeds China's standard seismic codes. To make it safe, engineers designed a system using megacolumns and massive trusses. These megacolumns are essentially enormous steel and concrete pillars that extend the full height of the building, bracing it against typhoon winds and earthquakes. The construction moved fast initially. Work began in August 2008. But just 4 months later, the global financial crisis hit. Goldin Properties halted work in January 2010, worried about cooling property markets in China and major investments struggling in Europe and the United States. The market recovered by 2011. Goldin decided to push forward, expecting to finish the tower and begin sales just as property prices reached their next peak. Construction resumed and picked up speed. By July 2014, the tower surpassed 440 meters. By September 2015, it reached its full structural height of 597 meters. Then came June 2015. The Chinese stock market crashed. Goldin Properties, which had borrowed heavily to finance the project, ran into severe financial difficulties. By December 2015, money ran out. China State Construction Engineering Corporation, the contractor, removed all workers from the site. The building stood complete on the outside, but hollow on the inside. No windows, no elevators, no electrical systems, no interior walls. The cost of what was built came to approximately $820 million just for the tower, with total development costs including the surrounding mall reaching $1.2 billion. That money sat frozen in an unfinished shell that couldn't generate any revenue. During the years that followed, Goldin Properties tried to revive the project. Brief restarts happened in 2016 and 2018, but each time work stopped again after just months. The building became a symbol of China's property bubble. In 2020, partly because of high-profile failures like Goldin Finance 117, the Chinese government banned construction of new buildings over 500 meters tall. Urban explorers made the abandoned tower famous in a different way. In 2015, 2 Russian and Chinese climbers scaled the tower and its construction crane. In 2016, Russian couple Ivan Birkus and Angela Nicolau climbed to the top and took photos that went viral on YouTube and Instagram. The empty tower became a magnet for daredevils seeking the ultimate roof-topping location. Meanwhile, the building's records slipped away. When it topped out in 2015, Goldin Finance 117 was the 5th tallest building in the world. The twisting Shanghai Tower and Pingan Finance Center in Shenzhen surpassed it while it sat empty. Today, if it ever opens, it will only be China's 3rd tallest and the world's 6th tallest. In April 2025, news broke that construction would resume. Tianjin's municipal government held meetings with China CITIC Group, China State Construction Engineering Corporation, and China Cinda to discuss revitalizing the project. A new construction permit was issued with a completion target of 2027. The $78 million permit doesn't list Goldin Properties anymore, suggesting the building will likely get a new name. The new financing details remain undisclosed, but experts believe the Chinese government is backing the restart with investment and debt restructuring. Why restart now after nearly 10 years? Professor Qiao Shitong from Duke University School of Law explains it's about signaling confidence. China's property market has struggled. Office vacancy rates are high, but the government wants to stabilize the sector. By having these projects revived and completed, the government at least hopes it can increase people's confidence, Qiao told reporters. The question is whether anyone will actually use the space. Shenzhen already has more office space than tenants. Tianjin, a second-tier city, has even less demand. During the decade, Goldin Finance 117 sat empty. Tianjin built the Tianjin CTF Finance Center, a 530-meter tower that's now the city's operational super tall. That building already struggles with occupancy. Still, if completed in 2027, Goldin Finance 117 will finally take its place in China's skyline. The walking stick design with its diamond crown will stand as a monument to both ambition and the risks of over-leveraged development. At 597 meters, it's tall enough to be impressive. The real question is whether those 128 floors. Before the Canyon Bridge, there was the Duge Bridge, which made history by becoming the first structure in the world to surpass the 500-meter height barrier many engineers thought was impossible. Standing 565 meters above the Baihetan River, it was the world's highest bridge from its opening in 2016 until 2025. The bridge deck sits higher above the ground than the Sears Tower is tall. Here, we can make an important distinction between the tallest and the highest when it comes to megabridges. A bridge's height is the maximum vertical distance between the ground and the bridge deck. Meanwhile, the tallest bridge refers to the height of the structure itself, starting from the base of the towers that hold it. That title still belongs to the Millau Viaduct in France, which is 343 meters tall. Before China's decision to build the Duge Bridge, engineers had for decades debated whether building a bridge at this height was even feasible. The extreme winds, the difficulty of construction, and the sheer engineering challenges seemed insurmountable. However, Dugan represents a fundamental shift in high bridge engineering, proving that cable-stayed designs could handle the most extreme conditions. The Duge Bridge is part of the G56 Hangzhou-Rili Expressway, a massive four-lane highway that stretches an incredible 2,935 kilometers from Hangzhou near Shanghai, all the way to the border of Myanmar near Tibet. This expressway crosses some of the most challenging terrain on Earth, requiring multiple record-breaking bridges along its route. The bridge connects Xuanwei City in Yunnan Province to Shucheng County in Guizhou Province. Before the bridge opened, the journey between these two cities took 4 to 5 hours of winding through mountain roads. The Duge Bridge reduced that journey to just over 1 hour, transforming transportation in the region. The bridge uses a cable-stayed design, where the deck is supported directly by cables connected to towers. The structure has a total length of 1,341 meters, with a main span of 720 meters stretching across the deepest part of the valley. The deck is made of a steel truss, a framework of interconnected steel beams that provides strength while keeping the weight manageable. The two towers are H-shaped and stand among the 30 tallest bridge towers in the world. The eastern tower measures 269 meters tall, while the western tower reaches 247 meters. Together, they support 112 pairs of stay cables arranged in a fan shape, each one precisely tensioned to distribute the load evenly across the structure. Construction began in 2011, but the project faced unique challenges from the start. The region's landscape is dominated by karst formations, limestone that has been eroded over millions of years, creating caves, sinkholes, and unstable rock. Engineers had to repeatedly move the planned location of the bridge higher and higher on the mountainside to avoid underground caves and areas where the rock was cracking or unstable. The Baihetan River Valley itself posed another problem. The gorge is so deep and the cliffs so steep that the river below is almost never directly illuminated by sunlight. This created severe temperature variations and wind patterns that engineers had to account for in the design. Wind was one of the most serious concerns. At 565 meters above the valley floor, the bridge deck often sits above the clouds and fog. Wind speeds at this altitude can be extreme, and engineers had to ensure the bridge wouldn't develop dangerous oscillations like those that destroyed the famous Tacoma Narrows Bridge in 1940. To test the design, engineers built scale models and subjected them to wind tunnel testing that simulated the specific conditions of the Baihetan River Valley. The aerodynamic shape of the steel truss deck was carefully refined to allow wind to pass through, rather than creating lifting forces or vibrations. The construction timeline stretched from 2011 to September 2016, when the bridge was finally completed. Workers had to build temporary access roads carved into the cliff faces just to reach the construction site. Just like the Canyon Bridge, some equipment and materials had to be transported by helicopter due to the extreme terrain. The bridge foundations required drilling deep into the mountainside bedrock. The tower foundations use group pile systems, clusters of concrete piles drilled dozens of meters into solid rock to anchor the massive towers against the forces generated by the suspended deck. Stringing the cables across the 720-meter main span was one of the most challenging phases. Workers used pilot cables, thin ropes shot across the gap, to pull progressively thicker cables until they could transport the main structural cables into position. The precision required was extraordinary, as even small errors in cable tension would create a wavy deck surface. The Duge Bridge officially opened to traffic on December 29, 2016. The total cost was approximately $144 million, a relatively modest sum for a structure of this scale and ambition. For its epic design, in 2018, the bridge won the Gustav Lindenthal Gold Medal at the 35th International Bridge Conference, often called the Nobel Prize of Bridge Construction. The same year, Guinness World Records officially certified it as the world's highest bridge, cementing its place in engineering history. Innovations used in building the Duge Bridge have been used in subsequent bridge projects across China and around the world. The Duge Bridge is more than just a record-breaking structure. It's part of China's strategy to develop its western provinces, which have historically been isolated by mountainous terrain. The Baihetan River Valley had been a barrier to transportation for thousands of years. The bridge erased that barrier in a single span. With this structure, China welcomed a revolution in engineering. In 1994, the country had just one bridge, over 122 meters tall. Today, the western provinces of Guizhou, Yunnan, Sichuan, and Hubei contain over 50 bridges exceeding 150 meters in height, including 10 of the world's 12 highest bridges. The Duge Bridge held the title of world's highest bridge for 9 years, before being surpassed by the Huajiang Canyon Bridge. However, the Duge Bridge's significance extends beyond its height record. It proved that cable-stayed bridges could handle the most extreme high-altitude conditions. It demonstrated that the 500-meter barrier could be broken, and it showed that even China's most remote and challenging terrain could be connected by modern infrastructure. The bridge remains a popular tourist destination, with observation decks at either end offering stunning views of the surrounding mountains and valleys. Photographers and engineering enthusiasts travel from around the world to experience the structure that seems to float above the clouds, connecting two provinces that were once separated by an impassable gorge. But it's only number 9 on our list, and the bridges ahead will push boundaries even further. Completed in 2022, Baihetan is the world's second-largest hydroelectric dam by capacity. It sits in a gorge so deep and narrow that standing at the bottom feels like being at the base of a vertical cliff that stretches up into the clouds. The Jinsha River has carved through solid rock here for millions of years, creating a canyon over 500 meters deep. This is where China built what might be the most technically sophisticated dam in the world. The dam rises 289 meters from its foundation, significantly taller than Three Gorges, and uses a double curvature arch design that makes it look like a massive concrete bow stretched across the canyon. This isn't just aesthetic. The arch transfers the enormous pressure of the reservoir into the canyon walls, rather than relying on the dam's mass to resist the water. It's an elegant solution to building in a confined space, but it requires the rock on both sides of the canyon to be absolutely solid. Any weakness in the canyon walls and the entire structure could fail catastrophically. What really sets Baihetan apart is the turbines. Each of the 16 turbines generates 1,000 megawatts, 1 gigawatt per turbine. These are the largest, most powerful hydroelectric turbines ever built. For comparison, the Three Gorges turbines max out at 700 megawatts each. Each Baihetan turbine could supply electricity to a city of several million people. The runner, the spinning part that the water pushes to generate power, weighs over 350 tons and has to spin at exactly the right speed while handling massive volumes of water flowing past at incredible velocity. The precision required is staggering. Any imbalance and the turbine would tear itself apart. Building something this powerful in a gorge this confined created engineering challenges that pushed the limits of what's possible with concrete. When concrete cures, it generates heat, a lot of heat when you're working with millions of cubic meters of it. This heat causes the concrete to expand, and then it contracts as it cools, creating cracks that can compromise the structure. In a dam where the concrete is under enormous stress from the water pressure, even small cracks can propagate into catastrophic failures. At Baihetan, engineers had to keep temperature differentials under control across 8 million cubic meters of concrete. They developed a new type of low-heat concrete that generates less warmth during curing, but even that wasn't enough. They embedded over 2,800 kilometers of cooling pipes throughout the dam, enough pipe to stretch from Beijing to Bangkok. Chilled water circulates through this network continuously, controlling temperatures during the years-long construction and curing process. It's like building air conditioning into the structure itself, except the room being cooled weighs tens of millions of tons. The location adds another layer of complexity. This gorge sits in one of the most seismically active regions in China. The 2008 Wenchuan earthquake, which killed nearly 70,000 people, originated not far from here. The dam had to be designed to withstand a magnitude 8 earthquake, ground shaking that would collapse most buildings, and still function. The arch design actually helps here because it can flex slightly during earthquakes, absorbing seismic energy rather than fracturing. But that meant anchoring the dam deep into bedrock on both sides of the canyon, drilling hundreds of meters down and injecting concrete to create a foundation that's effectively part of the mountain itself. Getting materials and equipment to the construction site was a logistical nightmare. The gorge is in mountainous terrain with few roads. Turbines weighing hundreds of tons had to be transported on specially reinforced trucks through narrow mountain highways with hairpin turns. In some cases, temporary access roads had to be carved into cliffsides just to reach the construction site. At peak construction, over 20,000 workers lived in camps built in whatever flat ground could be found or created near the gorge. Baihetan began generating power in 2021, with full operations starting in 2022. The dam produces about 62 billion kilowatt-hours annually, enough electricity to power a country the size of Norway. That power is transmitted eastward to coastal provinces via ultra-high voltage transmission lines that lose minimal energy even over distances of thousands of kilometers. The environmental and geopolitical implications mirror those of other Chinese megadams. On one hand, 62 billion kilowatt-hours of clean hydropower replaces coal generation that would produce 50 million tons of CO2 annually. On the other, the reservoir-submerged ecosystems displaced tens of thousands of people and disrupted fish migration routes. The Jinsha River becomes the Mekong as it flows into Southeast Asia, so dams here give China significant control over water resources that affect downstream countries. From a pure engineering standpoint, though, Baihetan represents China pushing the boundaries of what's possible with dam construction. They took lessons from Three Gorges, applied them in far more challenging terrain, and produced a structure that's more technically sophisticated in nearly every way. And Baihetan is just one dam in a whole cascade China is building along the Jinsha River. Which brings us to number 6, where things get even more extreme as we enter the world of China's insane hydropower stations. Shenzhen grew from a fishing village of 300,000 people in 1980 to a megacity of over 12 million by 2017. The city needed a symbol of that transformation. Pingan Insurance Company, one of China's largest financial firms, decided to build it. The Pingan International Financial Center stands 599 meters tall with 115 floors. It's the tallest building in Shenzhen, the second tallest in China, and the fifth tallest in the world. The tower opened in 2017 after 8 years of construction that pushed engineering to its limits. Design work began in 2008. American architectural firm Kohn Pedersen Fox created the concept while Thornton Tomasetti handled structural engineering. Both firms had experience with supertalls. KPF designed Shanghai World Financial Center, and Thornton Tomasetti worked on Shanghai Tower and Taipei 101. The foundation stone was laid in August 2009. Construction started that November on a challenging site. The building sits in Futian District's Central Business District, right next to Shenzhen Metro Line 1. Engineers had to dig deep foundations without displacing the subway tunnel by more than 10 millimeters, about the thickness of a smartphone. They solved this with an innovative cross-lot bracing system using 2 large-diameter rings. The first ring allowed construction of the tower's concrete core. The second ring provided access for removing 520,000 cubic meters of earth, enough to fill 200 Olympic swimming pools. The technique worked. The subway tunnel never shifted beyond acceptable limits. The tower's shape looks like a taut cable stretched between sky and ground. 8 composite super columns extrude beyond the building envelope, creating a distinctive ribbed appearance. At the top, the facades taper to form a pyramid. This isn't just aesthetic. The streamlined design reduces wind loads by 35 to 40%, critical for a city that faces regular typhoons. Shenzhen ranks among the world's cities most at risk for typhoon damage. Engineers designed a tube-in-tube structural system with the concrete core as the inner tube and the super columns forming the outer tube. 5 outriggers and 7 belt trusses connect the 2 tubes. Additional exterior diagonal bracing adds stability. To monitor all this, 428 sensors throughout the building form a structural health monitoring system. The sensors track stress, movement, wind loads, and temperature changes in real time. If anything shifts outside safe parameters, engineers can respond immediately. The facade uses 1,700 tons of stainless steel, the largest stainless steel facade in the world when completed. The specific grade is 316L, chosen for corrosion resistance. Shenzhen's coastal location means salty air that can rust normal steel within years. The 316L stainless steel will keep its appearance unchanged for decades. Construction hit a major crisis in March 2013. Workers suspected the concrete contained unprocessed sea sand, which can corrode steel reinforcement and make buildings unsafe. Authorities halted work immediately. Testing teams checked the concrete core multiple times. The tests eventually confirmed the concrete met specifications. Construction resumed in late March, but the incident caused delays and damaged confidence. Despite this setback, work proceeded quickly. By July 2014, the tower reached 443 meters and surpassed KK 100 to become Shenzhen's tallest building. 1 floor was added roughly every 4 days. The concrete core topped out at 555 meters on December 29, 2014. The full structure topped out in April 2015 at 599 meters. Originally, plans called for adding a 60-meter antenna that would have brought total height to 659 meters, making it taller than Shanghai Tower. In February 2015, the decision was made to cancel the antenna due to concerns it might obstruct flight paths near Shenzhen's airport. The building cost approximately $700 million to construct, remarkably economical. For comparison, the much shorter KK 100 cost more, and Shanghai Tower cost $2.4 billion. Part of the savings came from China's lower labor costs and efficient construction methods, but the design also optimized materials. The wind-reducing shape meant less structural steel was needed. The tower contains 33 double-deck elevators, traveling at speeds up to 10 meters per second. These were Shenzhen's first double-deck elevators. Each elevator car has 2 levels, effectively doubling passenger capacity. Installation required a team of specialized welders who set over 60,000 studs using a technique called stud welding. The first time this method was used for elevator installation in China, the contract specified that elevator vibrations couldn't exceed 10 milli-G, an extremely tight tolerance. With travel heights over 200 meters, achieving this required perfect installation. As one installer put it, 30% of ride quality comes from the product, 70% comes from installation. The top of the building houses an observation deck called Free Sky on floors 116 to 118. When it opened, the deck at 562 meters broke the world record for highest observation deck, beating the Burj Khalifa's deck at 555 meters. The deck offers 360-degree views and features interactive displays about Shenzhen's youth culture. Floors 109 through 112 serve as headquarters for Pingan Insurance Company, a Hyatt hotel signed on as anchor tenant in September 2013, occupying 20 floors below the headquarters levels. The lower floors contain office space, with the bottom levels dedicated to retail and conference facilities. The building connects directly to Shenzhen Metro Line 1 at Shopping Park Station. A large podium includes 5 floors of retail shops that terrace away from the tower, creating an amphitheater-like public space. The design pulls people into the building and creates pedestrian connections to neighboring properties. Goldin Finance Center stands so tall, it's visible from Hong Kong on clear days. People in Lantau Island, Shatton, and other parts of Hong Kong can see the tower rising across the border, dominating Shenzhen's skyline. At 599 meters and completed before China's 500-meter ban took effect, Goldin Finance Center represents one of the last opportunities to build this tall in China. The tower transformed Shenzhen's Fujian district into a world-class financial center. It provided Pingan Insurance with a headquarters befitting their status as one of the world's largest investment companies, and it created an icon visible from Hong Kong that announced Shenzhen's arrival as a global city. For a place that was farmland 4 decades ago, that's quite a statement. Moving east to Jiangsu Province, we arrive at a bridge that opened to traffic in September 2025 and immediately claimed multiple world records. The Changtai Yangtze River Bridge isn't just breaking one record, it's setting the standard for an entirely new category of infrastructure. The bridge stretches 10.3 kilometers across the Yangtze River, connecting the cities of Changzhou and Taizhou. Its main span measures 1,208 meters, making it the longest cable-stayed bridge in the world, surpassing the previous record holder, Russia's Russky Bridge, which has a main span of 1,104 meters. But length is only part of the story. What makes the Changtai Bridge truly revolutionary is that it's the first bridge on the Yangtze River to combine 3 different transportation systems in a single structure: an expressway for vehicles, a regular local road, and an intercity railway. This triple-function design represents a fundamental rethinking of how bridges can serve multiple purposes simultaneously. The journey between Changzhou and Taizhou used to take 80 minutes by road, winding around the Yangtze River. The Changtai Bridge reduces that journey to just 20 minutes. For the millions of people living in the Yangtze River Delta, one of China's most economically dynamic regions, this time, savings translates directly into increased productivity and economic opportunity. Construction of the bridge took 6 years, from 2019 to 2025, and required solving engineering problems that had never been encountered before. The total length of the road and rail section alone spans 5.3 kilometers, setting another world record for the largest continuous-length steel truss bridge. The bridge consists of several sections. The main cable-stayed section has that record-breaking 1,208-meter span over the primary navigation channel. 2 steel truss arch bridges, each with a 388-meter span, handle dedicated navigation channels. and a continuous steel truss bridge with three 124-meter spans covers non-navigable sections. Together, these components create a seamless crossing of one of the world's busiest waterways. The bridge towers rise 350 meters into the sky, roughly equivalent to a 120-story building. They're designed in a distinctive diamond shape and constructed from a combination of steel and concrete. This hybrid approach provides the stability needed to support the massive loads, while maintaining enough flexibility to handle temperature changes that can cause steel to expand and contract. The most innovative aspect of the Changtai Bridge is its asymmetrical lower deck design. Traditionally, engineers place the heavier railway in the center of the bridge with roads on either side. This balanced design distributes the weight evenly and simplifies the engineering. But in urban areas, this standard layout wastes valuable land because roadways often need to curve to connect to the city's network. The Changtai Bridge takes a different approach. On one side of the lower deck runs a high-speed railway capable of speeds up to 200 kilometers per hour. On the other side is a regular local road. This side-by-side arrangement saves land and provides more direct connections to the existing transportation networks in both cities. But this design created enormous engineering challenges. Railway sections can weigh up to 3 times as much as road sections. Placing all that weight on one side of the bridge creates uneven loading on the support cables, which could cause the deck to tilt or develop structural problems over time. The solution required extraordinary precision. Engineers, led by Qin Shunquan, chief scientist of the China Railway Group, had to carefully adjust the tension in each of the hundreds of cables supporting the railway side to keep the deck perfectly level. But adjusting the cable tension shifted the structure itself, misaligning its center line. The team had to develop computer models that could predict these effects and calculate the exact adjustments needed to keep everything aligned while under construction. The final connection of the main span required millimeter-level precision. When the two sides of the bridge met in the middle, the alignment had to be within 2 millimeters, less than the thickness of a coin. To achieve this, the construction team developed an intelligent decision-making system that monitored temperature, wind, and structural stress in real time, making constant micro-adjustments to keep everything aligned. The foundations of the bridge presented their own challenges. The Yangtze River at this location has powerful currents that constantly erode the riverbed. Engineers had to design and build massive underwater caisson foundations, essentially giant concrete boxes sunk to the riverbed and filled with concrete to create stable anchoring points for the towers. The project team set a new world record for the fastest sinking of a large caisson in a silty clay layer. They developed an intelligent airlift excavation system that could remove sediment from inside the caisson while it was being lowered, allowing for faster and more controlled sinking than traditional methods. Moving the massive steel truss segments into position required specially developed equipment. The team built the world's largest bridge deck crane, with a lifting capacity exceeding 10,000 ton-meters. This enormous machine could position bridge segments weighing hundreds of tons with millimeter-level accuracy, essential for maintaining the alignment of the entire structure. The stay cables themselves are engineering marvels. Some of them are exceptionally long and heavy, designed to handle not just the static weight of the bridge deck, but also the dynamic loads from trains traveling at 200 kilometers per hour and the constant traffic of vehicles. Each cable had to be precisely manufactured, transported to the site, and installed with exact tension specifications. Li Zhen, the project's chief engineer for the Jiangsu Transport Department, explained that the foundations were reinforced with extra strength specifically to resist the powerful currents of the Yangtze. The river flows 6,300 kilometers from the Tibetan Plateau to the East China Sea near Shanghai, making it Asia's longest river and the world's third longest. At this location, the current is strong enough to shift sediment and create significant lateral forces on the bridge foundations. The Changtai Bridge also incorporates cutting-edge technology in other ways. Engineers developed a satellite-guided tower crane system that used GPS positioning to place materials with high precision during construction. They built intelligent monitoring systems that continuously track the structural health of the bridge, measuring everything from cable tension to concrete stress to wind-induced vibrations. Officials say the bridge will significantly enhance connectivity and economic activity in the Yangtze River Delta. The region is already one of China's most important economic zones, home to major cities like Shanghai, Nanjing, and Hangzhou. The Changtai Bridge adds another critical link in the transportation network that ties these cities together. The bridge's completion in 2025 marks another milestone in China's systematic approach to building record-breaking infrastructure. Before the Changtai Bridge, the Russky Bridge in Vladivostok, Russia, held the cable-stayed span record at 1,104 meters since its completion in 2012. The Changtai Bridge extends that record by 104 meters, a jump of nearly 10%. This pattern repeats across China's bridge-building program. 6 of the 10 longest cable-stayed bridges in the world now span the Yangtze River, and all of them were built in the last 20 years. China isn't just building bridges, they're systematically pushing each bridge category to its limits and then finding ways to go even further. At 1,208 meters, the Changtai Yangtze River Bridge represents the current pinnacle of cable-stayed bridge design, but it's only number 8 on our list, and the bridges ahead will demonstrate even more ambitious engineering. While Baihetan grabbed headlines for its massive power output, there's another dam on the Duge River that might be even more impressive from a pure engineering standpoint. It's taller, it's built in more difficult terrain, and it's using construction techniques that didn't exist a decade ago. When engineers talk about building tall dams, they usually mean concrete structures anchored into bedrock. The Shuangjiangkou Dam takes a completely different approach. At 314 meters tall, it is one of the tallest rock-filled dams ever constructed. But height is just half the story. The Duge River carves through the eastern edge of the Tibetan Plateau in an area where mountains rise abruptly from narrow valleys, and earthquakes are simply part of life. The rock formations are fractured from millions of years of tectonic stress. Winter temperatures regularly drop below -20 degrees Celsius, making construction possible only during brief windows of decent weather. The nearest major city is hundreds of kilometers away over mountain roads that sometimes wash out completely during heavy rains. Conventional concrete dams in this terrain would be monumentally expensive and potentially unstable. Concrete requires massive amounts of water for mixing and curing. Cement has to be transported in, and the whole structure relies on having solid, unfractured bedrock to anchor into. Here, the bedrock is compromised in places, and getting materials to the site would multiply costs exponentially. Rock-filled dams solve these problems by using what's already there: rock. The concept is ancient, but executing it at this scale requires precision that would have been impossible a generation ago. You're essentially building an artificial mountain, but one that has to hold back billions of cubic meters of water without leaking, shifting, or collapsing. The Shuangjiangkou Dam contains 27 million cubic meters of material. Every single cubic meter had to be sourced from quarries, crushed to exact specifications, transported to the dam site, spread in layers no more than a meter thick, and then compacted using massive rollers until the density met strict requirements. Too much moisture in the fill and it won't compact properly. It'll settle over time and potentially fail. Too little moisture and the particles won't bind together adequately. The construction team had to monitor and adjust continuously based on weather conditions, rock characteristics, and the behavior of previously laid layers. The dam isn't just one uniform mass of rock. It's built in carefully designed zones, each serving a specific purpose. At the core is a watertight barrier made of clay and silt, extracted from specific deposits and processed to achieve the right consistency. This core has to be absolutely impermeable. Any leakage path through it could lead to internal erosion that undermines the entire structure. Surrounding the core are transition zones of progressively coarser material, each zone engineered to filter any water that might seep through, preventing it from carrying fine particles that would create voids. The outer faces are armored with massive boulders that protect against erosion from the reservoir and weathering from the elements. Building this in layers while maintaining stability creates a delicate balance. As you add height, the weight compresses the lower layers. That compression has to be uniform, or the dam will develop differential settlement, some parts settling more than others, which creates stress concentrations that can cause failure. Engineers monitored the dam constantly during construction using thousands of sensors embedded throughout the structure, measuring settlement, pore water pressure, and stress levels in real time. Seismic design was absolutely critical. This region experiences frequent earthquakes, and the dam had to survive a magnitude 8.0 event, ground shaking powerful enough to level most buildings. Rockfill dams have an advantage here because, unlike rigid concrete, rockfill can flex and absorb seismic energy without fracturing, but that only works if the design is right. Computer models ran thousands of simulated earthquakes, analyzing how different shaking patterns would affect the dam. The foundation was excavated deep into bedrock and shaped to optimize load transfer. Special drainage systems were installed to prevent water pressure from building up inside the dam during or after an earthquake. Construction began in 2014, and the challenges went beyond just engineering. The remote location meant building roads first, then establishing construction camps that could house over 10,000 workers in terrain that's inhospitable much of the year. They built concrete batch plants, equipment maintenance facilities, and power distribution systems, essentially creating a temporary industrial city in the mountains. Materials and equipment that couldn't be sourced locally had to be trucked in over mountain highways where a single breakdown could delay construction for days. The dam started impounding water in 2021, but full operations won't be achieved until 2025 as the reservoir gradually fills and the downstream cascade of dams comes fully online. At 314 meters tall, it creates a reservoir holding 2.7 billion cubic meters of water. The power output is 2,000 megawatts, which sounds modest compared to giants like Baihetan, but that misses the point of what Shuangjiangkou actually does. This dam sits at the top of a cascade system. Multiple dams stretch along the Dadu River below it, and Shuangjiangkou regulates the entire system. When downstream dams need more water to meet electricity demand, Shuangjiangkou releases it. During periods of heavy rain or snowmelt when too much water would overwhelm downstream facilities, Shuangjiangkou holds it back. It's flood control, power optimization, and water resource management all in one. Think of it as the conductor, making sure all the instruments in the orchestra play at the right time and volume. The strategic location matters too. The Dadu River Basin sits near Tibet and connects to the upper reaches of other major river systems. Control over water resources here translates to influence over water availability across a vast region, not just for hydropower, but for agriculture, drinking water, and industrial development. As climate patterns shift and water becomes more contested, projects like Shuangjiangkou become increasingly valuable beyond their immediate function. Environmental concerns about the cumulative impact of so many dams on one river system are legitimate. Fish populations have declined dramatically. The natural sediment flow that shaped the river and nourished downstream ecosystems for millennia is now interrupted. The river's flow regime is regulated by dam operators rather than natural seasonal variations, fundamentally changing how aquatic ecosystems function. China's calculation is straightforward. They need the power, they need the flood control, and they have the technology to build these structures safely in challenging environments. Shuangjiangkou demonstrates that capability. It's a rock-filled dam that rivals the height of concrete dams while operating in seismically active, high-altitude terrain. Still, as technically impressive as Shuangjiangkou is, it's about to be dwarfed both in scale and controversy by what's coming at number 5. Because the next project isn't just big, it's being built in one of the most remote, geologically unstable, and politically sensitive regions in the world. Guangzhou needed an icon. The city sits on the Pearl River Delta with 11.5 million people, but its skyline lacked a defining structure. In 2009, developer New World Development, a subsidiary of Chow Tai Fook Enterprises, held a competition to design a super tall that would change that. American firm Kohn Pedersen Fox won. They designed a 530-meter tower with 111 floors that would become known as the East Tower. The building opened in October 2016 and immediately became Guangzhou's tallest, China's 3rd tallest, and the world's 8th tallest. The tower sits in Zhujiang New Town, Guangzhou's central business district, on a 27,000 square meter lot along Zhujiang East Road. It's part of the Guangzhou Twin Towers. Across the central axis stands the 439-meter Guangzhou International Finance Center, known as the West Tower. Both towers have similar heights and functions, creating a balanced pair that frames the district's skyline. Groundbreaking happened on September 29, 2009, just 6 months after the design competition ended. China State Construction Engineering served as contractor. The tower topped out in July 2014. By the end of 2015, the exterior cladding was complete. The entire project took 7 years from design to opening. What makes this building stand out is its facade. The tower is wrapped in glazed terracotta, making it the world's tallest terracotta-clad building. The terracotta mullions create a lighter appearance than traditional glass and metal towers. Local environmental codes restrict how reflective glass can be, so standard solutions wouldn't work. Metal mullions could have achieved brightness, but architect Forth Bagley deliberately chose terracotta to inject into the architecture an indigenous craft that was specific to Guangzhou as a city. The material has practical advantages too. Terracotta is self-cleaning, which matters in a coastal city where salt air and pollution coat buildings quickly. It's corrosion-resistant, so it won't degrade over decades, and it's easily produced and shipped within China, reducing both costs and environmental impact from transportation. The shape changes as the tower rises. Different uses require different floor sizes, so the building tapers to accommodate those demands. The lower floors contain offices with larger floor plates. As you go higher, the building narrows for serviced apartments. The top floors house a luxury hotel with smaller footprints. This functional stacking creates the tower's distinctive silhouette, not just aesthetic choice, but practical necessity. Inside, the building mixes uses in a way that creates a vertical city. The basement and podium contain a massive shopping mall called K11 Art Mall, owned by K11, another Chow Tai Fook subsidiary. The mall occupies the entire 8-floor podium plus 2 basement levels, covering 70,000 square meters, about the size of 10 football fields. It features a 4DX cinema with 8 screens. Offices fill floors 7 through 43. These Grade A office spaces total about 209,000 square meters with flexible floor plates that support various business configurations. The offices include conference centers and modern amenities designed for multinational corporations. Serviced apartments occupy floors 49 through 70. These luxury residential units provide high-end living with hotel-style services, targeting executives and wealthy residents who want a home in the clouds. The Rosewood Hotel opened in spring 2019, taking over the top 16 floors plus podium spaces. A 5-star property with 365 rooms, the hotel puts guests at heights few other hotels can match. The top floors include amenities like rooftop pools and premium restaurants with views across the Pearl River Delta. Transportation connections run deep. Underground, the building links directly to public transit through basement-level connections. Pedestrian bridges at ground level connect to adjacent buildings, creating a network of climate-controlled walkways that let people move between structures without stepping outside. An underground parking facility holds 1,705 cars. The elevators are record setters. Hitachi designed 95 elevators that travel at speeds up to 72 kilometers per hour, some of the world's fastest. At that speed, passengers can go from ground level to the 111th floor in less than a minute. The building handles up to 30,000 people daily, so these high-speed elevators aren't luxury, they're a necessity. The construction moved at incredible pace. Guangzhou CTF Finance Center holds unofficial recognition as the fastest assembled supertall in history. Workers completed one floor roughly every 3 days during peak construction. This speed came from careful planning, prefabrication of components, and coordination between multiple teams working simultaneously on different levels. The structural system uses a composite design, combining a reinforced concrete core with steel elements. The core provides vertical load-bearing capacity and lateral stability. Steel framing around the perimeter allows for the irregular floor plates that change size as you ascend. The combination creates a rigid structure that can handle typhoons, earthquakes, and the settling that occurs in all tall buildings. Maintenance of a 530-meter tower requires specialized equipment. Rostec, a Finnish company, provided nearly 300 meters of concealed monorail track for building maintenance units. 2 self-powered platforms and a 10-meter motorized gantry allow workers to access every part of the exterior facade for cleaning and repairs. Some 42 meters of track remain visible, but most is hidden to preserve the building's clean aesthetic. The tower sits in a district that also includes the 604-meter Canton Tower, a telecommunications and observation tower that dominates the city's skyline. Together, the Canton Tower and the Guangzhou Twin Towers create a cluster of supertalls that announce Guangzhou's status as a major economic center. At 530 meters, the Guangzhou CTF Finance Center represents sophisticated urban planning. Not just a tall building, but a complete vertical neighborhood with shopping, working, living, and hospitality all stacked efficiently in one structure. The terracotta facade links modern engineering to traditional Chinese craftsmanship, creating something that's both futuristic and rooted in local culture. Just downstream from the Changtai Bridge, another record-breaking structure is taking shape. When the Zhangjingkou Yangtze River Bridge is completed in 2028, it will set 6 world records and become the longest suspension bridge ever built. The bridge will connect 3 cities, Zhangjiagang, Jingjiang, and Rugao, in Jiangsu Province. With a river-spanning length of 7,900 meters and a main span of 2,300 meters, it will surpass Turkey's Çanakkale Bridge, currently the world's longest suspension bridge with a main span of 2,023 meters by a full 277 meters. That 2,300-meter main span represents something historic. China will become the first country to break the 2,000-meter barrier for suspension bridges, achieving a span that many engineers considered impossible just a decade ago. Suspension bridges work differently from cable-stayed bridges. Instead of cables running directly from towers to the deck, suspension bridges feature a deck that hangs from vertical suspender cables. These suspenders connect to main cables that drape in a graceful curve between the towers and are anchored deep into the ground on either end of the bridge. This design allows suspension bridges to span much longer distances than cable-stayed bridges, but it also makes them more flexible and more susceptible to wind-induced vibrations. The longer the span, the more these challenges multiply. The first section of the bridge's main tower was hoisted into place in February 2024, marking the beginning of construction on what will become the world's highest suspension bridge tower. When completed, the towers will reach 350 meters into the sky, equivalent to a 125-story building. That's taller than most skyscrapers, and roughly the same height as the Zifeng Tower in Nanjing, Jiangsu's tallest building. These towers aren't just tall, they're also revolutionary in their construction. The Zhangjingga Bridge will be the first in the world to use a composite structure of steel box and concrete-filled steel tubes for the towers. Traditional suspension bridge towers are typically built entirely from concrete or entirely from steel. The hybrid approach combines the compressive strength of concrete with the tensile strength of steel, creating towers that are both lighter and stronger than conventional designs. This weight reduction is critical for a bridge of this scale. Lighter towers mean less load on the foundations, which translates to lower construction costs and faster build times. The composite design also provides better flexibility to handle thermal expansion and contraction, essential for a structure that will experience temperature variations of 50 degrees Celsius or more between winter and summer. The construction process for the towers demonstrates the precision required for modern mega bridges. Each tower segment weighs hundreds of tons and must be positioned with an accuracy of just 3 millimeters across 3 spatial dimensions. To achieve this, the construction team uses a 15,000-ton-meter tower crane combined with digital twin technology, a computer model that mirrors every aspect of the physical structure in real time. By September 2025, the North Tower of the South Navigation Span had surpassed 300 meters in height. Workers installed the T26 segment, which weighs 254 metric tons and stands 13.5 meters tall, at an altitude of 300 meters above the Yangtze River. The precision required at this height is extraordinary. Even small errors can compound as the tower grows taller. The foundation work for these massive towers required driving piles 97 meters long into the riverbed. Each pile is essentially a giant concrete column that anchors the tower to bedrock beneath the sediment of the Yangtze River. The south main tower base is designed in an octagonal shape with an area equivalent to 10 basketball courts. Workers poured 37,000 cubic meters of high-strength concrete just for the foundation, enough to fill 15 Olympic swimming pools. The main cables of the Zhangjingga Bridge will be the longest and strongest ever manufactured for a suspension bridge. Made from galvanized aluminum alloy high-strength steel wires, each cable consists of 247 strands with 127 wires per strand, each wire measuring 5.65 millimeters in diameter. The tensile strength of the steel is 2,200 megapascals, strong enough to support enormous loads while remaining flexible enough to handle the dynamic forces from wind and traffic. The bridge will have 184 pairs of hangers, the vertical cables that connect the main cable to the deck, spaced 16 meters apart along the entire length of the structure. Each hanger must be precisely manufactured and installed to ensure even load distribution across the deck. One of the most innovative features is the self-balancing structure system for the main cable. In traditional suspension bridges, the weight of the deck on one side of the tower must be balanced by the weight on the other side, creating complex engineering challenges during construction. The Zhangjingga Bridge uses a new system that allows the cables to balance themselves, simplifying construction and improving structural efficiency. The bridge will also feature super large-scale support transformation structure, composite ground anchor foundations. These massive concrete structures, buried deep in the ground at either end of the bridge, anchor the main cables and must resist pulling forces equivalent to the weight of hundreds of thousands of tons. The anchors are so large, they require developing entirely new construction techniques. The saddle structures, the curved supports where the main cables pass over the tops of the towers, will be the largest ever built for a suspension bridge. These saddles are prefabricated in sections and assembled on site, a first for structures of this scale. Each saddle must be machined to microscopic tolerances to prevent the cables from wearing or shifting over time. The entire bridge incorporates an integrated intelligent anti-corrosion system, another world first. The Yangtze River environment is humid and salty, creating ideal conditions for steel to rust. The anti-corrosion system uses sensors throughout the bridge to monitor moisture levels, temperature, and the chemical composition of the atmosphere, automatically adjusting protective measures to prevent deterioration. Construction on the Zhangjingga Bridge began in 2023, with completion scheduled for June 2028. The total investment is approximately 31.167 billion yuan, making it one of the most expensive infrastructure projects in China. The bridge deck will carry two-way 8-lane expressway traffic with a design speed of 100 kilometers per hour. When complete, the bridge won't just be a transportation link. It will fundamentally reshape the economic geography of central and southern Jiangsu province. The three cities it connects have historically been separated by the Yangtze, with ferry services and roundabout road routes limiting economic integration. The bridge will enable the kind of daily commuting and business interaction that drives modern economic growth. The 6 world records the Zhangjingga Bridge will set include the longest suspension bridge span, the tallest suspension bridge tower, the longest high-strength main cable, the largest composite ground anchor foundation, the largest continuous-length steel box girder, and the largest displacement expansion device. These records aren't just about bragging rights. Each one represents a genuine breakthrough in engineering capability. Chinese engineers and officials describe the Zhangjingga Yangtze River Bridge as a landmark project for Jiangsu Province, a representative project for China's bridge technology innovation, and a milestone project for the construction of super-large span suspension bridges. It demonstrates the innovative achievements of continuous exploration and breakthroughs in Chinese bridge construction. At 2,300 meters, the Zhangjingga Bridge main span is 900 meters longer than the Nanjing-Qiqiaoshan Yangtze River Bridge, itself a record breaker when it opened. The jump from 2,023 meters to 2,300 meters might seem modest, but at this scale, Every additional meter of span creates exponentially more difficult engineering challenges. The bridge is only number 7 on our list, but it's already pushing the boundaries of what's considered physically possible for suspension bridge construction. The structures ahead will demonstrate that China's bridge-building ambitions extend even beyond breaking the 2,000-meter barrier. There are places on Earth where building anything is almost suicidal. Medog County, deep in Tibet on the edge of the Himalayas, is one of those places. It's where the Yarlung-Tsangpo River makes a dramatic bend, the Great Bend dropping through one of the deepest gorges on the planet. And China is building what could become the world's largest hydropower station right there. Let's talk about why this is insane. The Yarlung-Tsangpo River flows relatively peacefully across the Tibetan Plateau until it reaches the eastern Himalayas. Then it encounters a wall of mountains and is forced to turn nearly 180 degrees, carving a gorge that plunges over 5,000 meters from rim to bottom, almost twice as deep as the Grand Canyon. In a short stretch, the river drops 2,000 meters in elevation, creating some of the world's most powerful rapids and waterfalls. That elevation drop represents enormous hydroelectric potential. Gravity is pulling that water down with tremendous force. Capture that energy, and you could generate power on a scale that makes even Three Gorges look modest. The estimated capacity? Around 60,000 megawatts. That's nearly 3 times the output of Three Gorges. It would be the most powerful hydropower station on Earth by a massive margin, but building it requires solving problems that seem almost impossible. First, there's the geography. Medog County was the last county in China to be connected by road, and that road is only open part of the year due to landslides and snow. The terrain is so steep and unstable that simply accessing the construction site requires tunneling through mountains for kilometers. The bedrock is fractured from tectonic activity. Landslides are common. The area receives some of the heaviest rainfall in China, which triggers constant erosion. Then there's the seismic risk. This region is where the Indian tectonic plate is colliding with Eurasia, pushing up the Himalayas at about 5 millimeters per year. Major earthquakes are not a question of if, but when. The 1950 Assam earthquake, which struck nearby, was magnitude 8.6 and caused entire mountainsides to collapse. Building a massive dam in this environment means designing for worst-case scenarios that would destroy conventional structures. The engineering solution involves building not one giant dam, but a series of smaller dams and underground powerhouses connected by tunnels carved through the mountains. Instead of fighting the terrain, the design works with it. Water would be diverted through massive tunnels, dropping through turbines housed in caverns carved into solid rock, then continuing downriver to the next station. These aren't small tunnels. We're talking about water tunnels over 10 meters in diameter, stretching for tens of kilometers through tectonically active mountains. Each tunnel has to be lined with concrete and steel, reinforced to withstand earthquakes and the immense pressure of water flowing at high velocity. The powerhouses themselves would be underground massive caverns excavated from bedrock, housing turbines that each generate thousands of megawatts. Building these caverns requires removing millions of cubic meters of rock, all while ensuring the caverns remain stable in rock that's under enormous tectonic stress. Construction timelines are ambitious. Official reports suggest the project could begin major construction in the mid-2000s, with completion by the 2030s. But those timelines are speculative. The preparatory work alone, building access roads, conducting geological surveys, excavating exploratory tunnels, takes years in this terrain. And then there's the politics. The Yarlung-Tsangpo becomes the Brahmaputra River as it flows into India and Bangladesh. A dam of this scale would give China enormous control over water flowing to 2 countries that together have over 1.5 billion people. India has already expressed concerns. Environmental groups point out that the ecological impact on the Brahmaputra basin could be catastrophic. China's position is that the dam is for power generation, not water control, and that it won't significantly affect downstream flow. But that's a hard sell when you're talking about the world's largest hydropower project on an internationally shared river. Domestically, the project is controversial too. Meidog is home to unique ecosystems found nowhere else on Earth. The gorge's depth creates multiple climate zones, from subtropical rainforest at the bottom to alpine conditions at the top. Species that evolved in isolation could be threatened by construction and the altered river regime. There's also the question of cost. Estimates range from $80 billion to over $100 billion, making it potentially the most expensive infrastructure project ever attempted. For perspective, that's more than the entire GDP of many countries. Critics question whether it's even necessary. China already has massive hydropower capacity. Solar and wind are becoming cheaper. Why risk a project of this complexity and controversy? Supporters argue that hydropower is dispatchable. It can generate electricity on demand, unlike solar and wind. As China transitions away from coal, it needs reliable baseload power. A 60,000 megawatt hydropower station could stabilize the entire national grid. The Meidog hydropower station is still in early stages, and it's possible the project could be scaled back or even canceled if challenges prove insurmountable. But if China commits fully, it will be one of the most ambitious engineering projects ever attempted. Yet, even this isn't the biggest water project on our list. Because while Meidog is about generating power, the projects coming up are about moving water itself on a scale that's hard to fathom. But first, we need to go underwater. In the Tianjin Economic Technological Development Area, about 150 kilometers from Beijing, engineers built a tower that looks like it's melting. The Tianjin CTF Finance Center, completed in 2019 with a distinctive curved glass skin that gently undulates as it rises 530 meters into the sky. At exactly the same height as its sister building in Guangzhou, 530 meters, this tower takes a completely different approach to design and construction. Both are owned by Changtai Fook Enterprises, but the similarities end there. Skidmore, Owings and Merrill designed the Tianjin Tower in collaboration with Ronald Liu and partners. The brief called for a mixed-use building in Binhai New Area, a district positioned to become Tianjin's new financial center. The city has 13 million people, China's fifth largest metropolis, and a major port on the Bohai Sea. Groundbreaking happened on November 20th, 2009. Full construction began on January 3rd, 2013. The project took 6 years of active construction, finally reaching substantial completion on September 22, 2019. The tower has 97 floors, making it the tallest building in the world with fewer than 100 floors. The building's shape comes from practical requirements. The tapering form, created by reducing floor plate sizes as you ascend, minimizes surface area exposed to wind, sun, and moisture. This matters in Tianjin, where winter temperatures drop below freezing and summer typhoons batter the coast. 8 sloping mega columns curve around the building's exterior, following a line that connects the centers and corners of all 4 elevations. These mega columns aren't decorative. They're integral to both the gravity and lateral systems, meaning they carry the building's weight while also resisting sideways forces from wind and earthquakes. Tianjin sits in a high seismic zone. The mega columns increase stiffness in the building's perimeter frame, pulling a larger portion of seismic forces away from the core. Chinese building codes require this for structures in earthquake-prone regions. The curving columns also create natural stiffness at the building's base, where lateral loads concentrate most heavily. The undulating curves serve another purpose: confusing the wind. When wind hits a rectangular building at consistent speed, it creates a phenomenon called vortex shedding. The wind separates on either side of the building and forms swirling vortices that can set up resonant vibrations. In extreme cases, this can cause catastrophic structural failure. The Tianjin Tower's curves disrupt this pattern. The aerodynamic shape prevents vortices from forming consistently, dramatically reducing wind forces on the structure. The building also features strategically placed multi-story wind vents and a porous crown that lets air pass through rather than building up pressure. By optimizing the structural design, SOM's integrated architecture and engineering team dramatically reduced the steel required for construction. These material savings had multiple benefits. Less steel meant less weight, which reduced seismic forces on the foundation. It eliminated the need for a separate dampening system, a massive pendulum or liquid-filled tank that many supertalls require to prevent swaying. The reduced construction time and cost made the project economically viable despite its extreme height. The construction timeline hit key milestones rapidly. In July 2016, the concrete core reached 260 meters. In April 2017, the structure topped out. On October 31, 2017, workers installed the distinctive steel crown atop the building, completing the upper envelope and reaching the full 530-meter height. The building used building information modeling extensively, one of the early super-tall projects to integrate BIM with IoT sensors and RFID tags throughout construction. This technology allowed real-time tracking of construction elements and automatically alerted teams to potential conflicts between structural, mechanical, and electrical systems. The approach reduced rework and improved efficiency in a project with thousands of components being assembled simultaneously. The foundation required deep piles driven 97.5 meters into the ground, with an effective pile length of 71.2 meters. Each pile can handle a vertical compressive load of 12,700 kilonewtons, roughly equivalent to the weight of 1,300 cars stacked on a single point. The building cost approximately $1.2 billion to construct. Efficient for a structure of this scale and complexity, much of that efficiency came from the optimized structural system that reduced material use while maintaining safety margins well above code requirements. While the new Tianjin district was one of China's first state-level economic zones, it lacked a defining landmark. The CTF Tower provided that identity, visible for kilometers across the flat coastal plain. The Tianjin CTF Finance Center and the one in Guangzhou prove that two buildings at exactly the same height can tell completely different stories. One uses terracotta to connect with local tradition. The other uses curves to battle physics. Both reach 530 meters, but they got there by solving different problems in different places for different purposes. That's the real achievement, not the height itself, but the intelligence behind it. While the Zhangjingga Bridge soars high above the Yangtze River on the world's tallest towers, our next megaproject takes an entirely different approach. The Shenzhen-Zhongshan Link doesn't just cross water, it dives beneath it, disappearing into one of the most ambitious underwater tunnels ever constructed. The Shenzhen-Zhongshan Link opened to traffic on June 30, 2024, after 7 years of construction that pushed engineering to its limits. This isn't a simple bridge. It's a 24-kilometer cross-sea passage that combines 2 bridges, 2 artificial islands, and a massive underwater tunnel to connect the technology hub of Shenzhen to the industrial city of Zhongshan across the Pearl River estuary in Guangdong Province. Before this link opened, traveling between Shenzhen and Zhongshan required a 2-hour journey winding around the Pearl River. The new crossing reduces that to just 30 minutes, fundamentally transforming transportation in the Guangdong-Hong Kong-Macau Greater Bay Area, one of the most economically dynamic regions in the world. The project cost approximately $4.83 billion and represents one of the most complex cross-sea construction projects ever attempted. It sits about 32 kilometers north of the Kong-Zhuhai-Macau Bridge and 27 kilometers downriver from the Human Bridge, creating a network of crossings that stitch together the cities on both sides of the Pearl River estuary. What makes this project particularly remarkable is that it combines 3 completely different types of infrastructure in a single crossing. The journey starts with the Shenzhen-Zhongshan Bridge, a massive suspension bridge with a main span of 1,666 meters and towers reaching 270 meters high, equivalent to a 90-story building. This section provides a navigation clearance of 76.5 meters, the highest for any sea bridge in the world, allowing even the largest cargo ships to pass beneath. The suspension bridge then connects to an artificial island in the middle of the Pearl River estuary. This island is 625 meters long and 456 meters at its widest point, with a total area of 137,000 square meters, equivalent to 19 international standard football fields. Building this island required solving problems that had never been encountered at this scale before. The Pearl River estuary has water depths of over 40 meters in some areas, with a seabed consisting of thick layers of soft mud interspersed with hard soil layers. Traditional island construction methods wouldn't work. Engineers developed a technique using 57 giant steel cylinders, each 28 meters in diameter, roughly the size of a basketball court. These cylinders were prefabricated in factories, transported to the site, and driven deep into the seabed using specialized equipment. But the hard soil layers beneath the mud presented a challenge. The team developed a deep slurry mixing technology that used a special ship to penetrate the hard layers like a giant blender, mixing in materials to soften the soil and allow the cylinders to be positioned accurately. Once the cylinders formed a ring around the perimeter of the island, ships pumped millions of cubic meters of sand into the center, causing land to emerge from the sea in a kite-like shape. From the western artificial island, the crossing transforms into an underwater tunnel. This isn't just any tunnel, it's the world's longest and widest underwater steel shell concrete immersed tube tunnel, stretching 6.8 kilometers beneath the Pearl River. The tunnel consists of 32 massive prefabricated sections, each weighing 80,000 tons, plus a final joint section connecting them all. Each tunnel section is essentially a giant steel box filled with concrete. Manufacturing these required building a specialized smart factory in Zhuhai that took 10 months to upgrade. The factory produced 23 tunnel sections, patenting 11 inventions in the process. The sections are 180 meters long, making them the largest tunnel segments ever manufactured for an immersed tube tunnel. Getting these enormous sections into position required developing entirely new equipment. Engineers built the Yinjiang-Buhan, the world's first integrated self-propelled transport and installation vessel for immersed tubes. This 20,000-ton ship can carry tunnel sections over 50 kilometers of open water and position them on the seabed with millimeter precision. The installation process is extraordinarily complex. Each section had to be floated to the construction site, carefully ballasted to achieve neutral buoyancy, then slowly lowered 40 meters to the seabed where it connects to the previous section. The precision required is incredible. If the sections don't align within a few millimeters, the tunnel won't seal properly and water will leak in. To achieve this precision, engineers introduced the Beidou satellite navigation system for the first time in cross-sea tunnel construction. The satellite system provides real-time positioning accurate to within centimeters, allowing the installation vessel to adjust its position continuously as it lowers each massive tunnel section into place. The entire floating installation of a single section takes about 10 hours. The tunnel itself is an engineering marvel of safety systems. 14 robots constantly patrol the 6.8-kilometer length, monitoring pipes and cables, detecting potential problems, and even managing traffic during accidents. The robots can direct vehicles using built-in loudspeakers and film incidents while transmitting video to a remote control center. The lighting system inside the tunnel is particularly innovative. Under normal conditions, the walls glow green, but during emergencies, they turn red. The system can also create a progressive color change from yellow to green, guiding people toward exits during evacuations. Intelligent lighting control adjusts brightness automatically based on traffic conditions and time of day, reducing driver fatigue during the underwater journey. Fire safety was a critical concern for a tunnel this long beneath the water. Engineers developed a horizontal smoke exhaust system at the top of the tunnel that improves smoke evacuation efficiency by 42% compared to traditional systems. The tunnel also features dual wavelength flame detectors and an advanced firefighting system designed specifically for ultra-wide underwater tunnels with interchange sections. After emerging from the tunnel at another artificial island, the crossing continues with the Zhongshan Bridge, a cable-stayed structure that uses a different design than the suspension bridge on the other end. The cable-stayed section transitions smoothly to the mainland through carefully designed approach roads. The bridge deck itself uses specialized materials. The steel surfaces are coated with hot mix epoxy asphalt that's flexible enough to accommodate the movement of steel in changing temperatures, yet strong enough to withstand heavy truck traffic. Inside the tunnel, the pavement uses fire-resistant asphalt as an additional safety measure. The Shenzhen-Zhongshan Link officially claims 10 world records, though many of them are highly specific. They include the largest span for a fully offshore steel box girder suspension bridge, the highest navigable clearance for a sea bridge, the largest offshore suspension bridge anchorage, the world's longest and widest underwater steel shell concrete immersed tube tunnel, the largest single-volume concrete pour for a steel shell immersed tube section, the world's first underwater expressway interchange, and the widest repeatedly foldable M-shaped water stop used in an immersed tube tunnel final joint. In April 2024, before the link even opened, the Shenzhen-Zhongshan Bridge won the George S. Richardson Medal at the International Bridge Conference, often called the Nobel Prize of Bridge Engineering. This recognition came for the bridge's excellent quality and innovative construction techniques. Since opening in June 2024, the link has been enormously popular. In the first month of operation, more than 3 million vehicle crossings were recorded. The crossing has become so popular that congestion sometimes develops, with some drivers reporting hours-long waits during peak periods. But for most users, the ability to cross the Pearl River estuary in half an hour instead of 2 hours represents a transformation in regional connectivity. The Shenzhen-Zhongshan Link is part of a broader strategy to integrate the Guangdong-Hong Kong-Macau Greater Bay Area, a region covering 56,000 square kilometers with a population exceeding 70 million people. The area generated economic output of over 14 trillion yuan, approximately $1.96 trillion in 2023. China aims to develop it into a world-class city cluster and global technology center. At $4.83 billion and 24 kilometers long, with a tunnel that accounts for nearly 7 kilometers of underwater passage, the Shenzhen-Zhongshan Link demonstrates how modern engineering can overcome geography that once seemed impassable. But even this ambitious project pales in comparison to what comes next. Our next bridge doesn't cross the widest river or dive the deepest underwater. Instead, it conquers something engineers once considered impossible, spanning a river valley using only a single tower on one side. And it does this in one of the most remote and mountainous regions of China, where the construction site itself sits 320 meters above the assembly yard below. Imagine drilling a tunnel under the ocean, connecting two cities separated by one of China's busiest shipping lanes. Now imagine that tunnel is 123 kilometers long, longer than the Channel Tunnel connecting England and France, and runs under waters that are, in places, over 100 meters deep. That's the Yantai-Dalian Undersea Tunnel, and it's not just an idea anymore. Planning is advanced, and if completed, it will be the longest undersea tunnel in the world. Here's why it matters. The Bohai Sea sits between northern China's Liaodong Peninsula and the Shandong Peninsula. It's a relatively shallow body of water, but its wide crossing from Dalian in the north to Yantai in the south requires either a long drive around the coast or a ferry ride that takes several hours. That geography creates a bottleneck. Road freight traveling from China's northeast to the rest of the country has to go the long way around. The ferry system helps, but it's limited by weather, can't operate in rough seas, and has finite capacity. For an economy that moves as much freight as China's, that bottleneck costs time and money. The solution? Tunnel under the Bohai Sea. The tunnel would run about 123 kilometers from shore to shore, making it roughly 50% longer than the Channel Tunnel. But unlike the Channel Tunnel, which runs through stable chalk bedrock, the Bohai Tunnel would pass through sediment, sand, and soft rock in a seismically active region that's also prone to strong ocean currents and winter ice. Engineering this tunnel requires solving problems that would make most engineers walk away. First, there's the length. Boring a tunnel 123 kilometers long is a logistical nightmare. Tunnel boring machines, TBMs, are enormous, the size of apartment buildings, and they can only bore in one direction. For a tunnel this long, you'd need multiple TBMs, starting from different points and meeting in the middle with millimeter precision. Any misalignment and the tunnels don't connect. The depth is another issue. In the deepest sections, the tunnel would run about 100 meters below the seabed, which itself is under 100 meters of water. That means the tunnel is under immense hydrostatic pressure. Water wants to get in. The rock and sediment want to collapse. Keeping the tunnel stable requires constant reinforcement with concrete linings, steel ribs, and sophisticated drainage systems to manage groundwater. Then there's ventilation. A 123-kilometer tunnel carrying vehicle traffic would generate massive amounts of exhaust fumes. Those fumes have to be removed and fresh air pumped in, requiring ventilation shafts and enormous fans capable of moving air through a confined space over 100 kilometers long. The tunnel would likely be built with two main tubes, one for each direction of traffic, plus a service tunnel in the middle for maintenance and emergency access. That's essentially building three separate tunnels simultaneously. Escape and safety are critical concerns. If there's a fire or accident in the tunnel, people need a way out. But you can't just open a door and leave. You're 100 meters underground beneath the ocean. The design would need emergency exits every few kilometers, connecting to the service tunnel with pressurized safe zones where people can wait for rescue. Earthquakes are a real risk. The Bohai region isn't as seismically active as some parts of China, but significant earthquakes do occur. The tunnel has to be flexible enough to handle ground movement without cracking or collapsing. That means joints, expansion gaps, and materials that can absorb seismic energy. The economic case for the tunnel is compelling. Current travel time between Dalian and Yantai is around 8 hours by land or ferry. The tunnel would cut that to under 2 hours. Freight costs would drop dramatically. The entire region would become more economically integrated. Cost estimates vary wildly, from $36 billion to over $50 billion, depending on the final design and construction method. That's enormous, but China has been willing to spend comparable amounts on other infrastructure projects. Construction timelines are still uncertain. Official planning has been ongoing for years, with various feasibility studies and route options analyzed. Some reports suggest construction could begin in the mid-2000s, with completion in the 2030s. But a project of this complexity could easily face delays. Critics question whether the tunnel is necessary. High-speed rail already connects the region, albeit indirectly. The ferry system works, even if it's slow. Is a $50 billion tunnel really the best use of resources? Supporters point to the long-term economic benefits. Infrastructure doesn't just serve today's needs, it enables tomorrow's growth. A tunnel that cuts travel times and freight costs could pay for itself over decades by enabling economic activity that wouldn't otherwise happen. There's also the prestige factor. Completing the world's longest undersea tunnel would be a statement of China's engineering prowess, joining projects like Kong-Zhuhai-Macau Bridge as symbols of what the country can achieve. The Yantai-Dalian undersea tunnel is still in planning stages, and it's possible the project could be modified or even shelved if challenges prove too great. But if it moves forward, it will push tunneling technology to new limits. Of course, drilling under the Bohai Sea is impressive, but it's nothing compared to drilling through mountains to move water across an entire province. That's where number 3 comes in. In the heart of Beijing, a new giant reshaped the skyline and challenged everything the city thought was possible. Standing at approximately 530 meters, China Zun, also known as the CTF Tower, is the tallest building in the capital. But more than its height, what makes this tower extraordinary is the story behind how it was built. A tale of ambition, engineering ingenuity, and the delicate balancing act of constructing a super-tall skyscraper in one of the world's most politically and culturally sensitive cities. The story begins in 2011, when Beijing was cautiously opening its doors to super-tall development. Height restrictions had long dominated city planning, a safeguard against both aesthetic disruption and seismic vulnerability. The approval process alone required negotiation at the highest levels of municipal government. Planners wanted a statement, a building that would declare Beijing's economic power, but one that would also respect the city's traditions. The resulting compromise gave birth to the unusual form of China Zun, a shape inspired by an ancient Chinese wine vessel, wide at the base, narrow in the middle, and expanding again near the top. Elegant to the eye, this design was a nightmare to build. Early construction began with a focus on the foundation, a critical challenge in Beijing's clay-heavy soil. Engineers poured thousands of tons of high-strength concrete, extending deep into the bedrock. The foundation itself was a feat of precision. Any miscalculation at this stage could compromise the entire tower. Workers labored under strict quality controls, monitoring every pour, every beam, and every anchor. This painstaking preparation delayed the start of vertical construction, but ensured that the superstructure would rise safely above the city streets. Once construction above ground began, the real drama unfolded. China Zun's unusual shape presented structural challenges that demanded advanced solutions. To resist strong winds and earthquakes, engineers designed a megaframe system combined with outrigger trusses, connecting the reinforced concrete core to the perimeter columns. In simple terms, imagine a giant spine linked to ribs, allowing the building to sway slightly in extreme conditions without breaking. Invisible from the street, but essential for safety, especially given the tower's height, which subjects it to wind speeds far higher than those at ground level. Adding to the complexity, China Zun incorporated cutting-edge construction technology. Vertical cranes had to operate near their maximum capacity, lifting steel beams and prefabricated floor sections hundreds of meters into the air. Logistics planning became a science. Materials were sequenced with military precision, just-in-time delivery was critical, and scheduling accounted for wind, rain, and the seismic sensitivity of the soil. Every day, engineers calculated how the building would move, how much it would twist under wind pressure, and how stresses would transfer from the exterior to the core. For a building of this scale, minor errors could become catastrophic. As the tower rose, the pace slowed, not from incompetence, but from deliberate caution. At over 500 meters, even a small deviation could jeopardize safety. Floor after floor, workers monitored vertical alignment, load distribution, and material integrity. Concrete had to cure precisely. Cranes had to operate at optimal wind conditions, and every beam placement was double-checked. This was not a race. It was a methodical ascent into the clouds. The tower finally topped out in 2018, 7 years after construction began. But topping out is only the beginning for a building of this magnitude. Interior fit-out, mechanical systems, elevators, safety certifications, and tenant installations took another year. China Zun officially opened around 2019, marking nearly a decade of continuous planning, design, and construction, a timeline that reflects both the ambition and caution required to deliver such a skyscraper in Beijing. The sheer scale of the building is staggering. With 108 floors, each level is home to offices, observation areas, and mechanical equipment. From the ground, it can feel almost impossible to take in. For comparison, the tower is taller than the Empire State Building, yet with a slimmer, more elegant profile. The widening at the base and top creates the illusion of stability while adding usable space, a perfect marriage of aesthetics and functionality. China Zun was also a massive financial undertaking. Estimated costs ran into the several billion-dollar range, a figure that reflects not just the structure itself, but also the planning, technology, and risk management embedded in every phase. From the city's perspective, this investment was about more than office space. It was a declaration. Beijing could host super-tall buildings with the same technological sophistication as Shanghai, Shenzhen, or Hong Kong. Today, China Zun is more than a skyscraper. It is a symbol of national ambition. Its reflective glass catches the sunrise over Beijing. Its curved silhouette dominates the skyline, and its interior hums with the operations of multinational corporations. And yet, much of its impact is invisible. In the careful engineering decisions, the precise concrete pours, the mega-frame spine that allows it to dance with the wind, and the relentless coordination of workers, engineers, and architects over nearly a decade, China Zun is a narrative written not just in steel and concrete, but in every decision that allowed the tallest building in Beijing to rise safely, elegantly, and permanently into the sky. Moving from the coastal plains of Guangdong to the rugged mountains of Yunnan province, we encounter a bridge that breaks every conventional rule of suspension bridge design. The Lujiang Bridge, which opened in April 2022, is the world's first single-tower, single-span suspension bridge, a structure that physics textbooks once suggested was impossible. The bridge stretches 798 meters across a V-shaped canyon carved by the Lujiang River, whose name translates literally as Green Juice River. The main span between the tower and the opposite mountainside anchoring point measures 780 meters, surpassing the previous single-tower record of 766 meters held by the Jinshajiang-Hutia-Oxia Expressway Bridge. But the span measurement doesn't capture what makes this bridge extraordinary. Traditional suspension bridges use towers on both sides of the gap, with cables draped between them supporting the deck. The Lujiang Bridge uses only one tower on one side, with the cables anchored directly into the mountain on the opposite side. There are no additional support columns anywhere. The entire 798-meter length hangs in space, supported by cables attached to a single tower and a tunnel anchorage carved deep into solid rock. The bridge is located in central Yunnan province, connecting Yuxi City and the Chuxiongyi Autonomous Prefecture. Before the bridge opened, crossing from one side of the valley to the other required a 1.5-hour journey through winding mountain roads. The Lujiang Bridge reduces that journey to 2 minutes, with vehicles traveling across at speeds up to 100 kilometers per hour. Construction began in 2019 and took 3 years to complete, a relatively short timeline for such an innovative structure. But every phase of construction presented challenges that had never been faced before. The most immediate problem was the terrain itself. The bridge is built in a V-shaped canyon with near-vertical cliffs on both sides. The bridge deck sits 320 meters above the valley floor, where the construction assembly yard had to be located. That's equivalent to a 100-story building. Getting materials and equipment up those cliffs required building temporary access roads carved into rock faces so steep that trucks could barely navigate them. The single tower rises 156 meters from its foundation and stands on a steep mountainside rather than flat ground. Every component of the tower had to be transported up the mountain and assembled piece by piece in a location where there was barely room to maneuver equipment. Workers operated at heights and angles that would be considered extreme, even by mountaineering standards. The opposite side of the canyon presented an even greater challenge. Without a tower on that side, the main cables must be anchored into the mountain itself. Engineers designed what they claim is the world's steepest tunnel anchorage, carved into solid rock at an angle of 54 degrees. The tunnel extends deep into the mountain, with the cables splayed out inside and locked into massive concrete anchor blocks that transfer the pulling forces into the surrounding bedrock. The steel box girder deck weighs approximately 10,000 tons, equivalent to the weight of the Eiffel Tower. This entire mass hangs from cables attached to the single tower, creating enormous stress concentrations. The tower must resist not only the downward force of the deck's weight, but also the horizontal pulling forces from the cables. To handle these forces, the tower is built from reinforced concrete with a carefully designed cross-section that distributes stress evenly. The foundation extends deep into the mountainside, with dozens of piles drilled into bedrock to anchor the tower against the pulling forces that try to topple it. The deck consists of 61 prefabricated steel box girder segments, each manufactured in the valley below and then hoisted up to the bridge level. The maximum weight of a single segment exceeds 180 tons. Lifting these massive steel sections 320 meters vertically required specialized cranes and rigging systems designed specifically for this project. On March 9, 2022, workers installed the final deck segment, completing the closure of the bridge. This was a critical moment. If the two ends of the deck meeting in the middle didn't align within a few millimeters, the entire structure would need adjustment. The precision achieved after 3 years of construction in one of the most challenging environments in China was a testament to careful planning and skilled execution. The bridge emerges from tunnels on both sides of the canyon, adding to its dramatic appearance. Vehicles approaching from either direction drive through a mountain tunnel, then suddenly burst into open air high above a river valley with nothing but sky and mountains visible ahead. The tunnel-to-bridge transitions were carefully designed to prevent drivers from being suddenly blinded by sunlight after the darkness of the tunnels. The Lujiang Bridge is part of the 190-kilometer Yuchu Expressway, which connects Yunnan to other major national highways, including the Hangzhou-Ruili Expressway running to a city on the Myanmar border, and the Guangzhou-Kunming Expressway linking the coast to the interior. The bridge is also a critical component of Yunnan's 9,000-kilometer provincial highway network. Neither Yangtze City nor the Chuxiongyi Autonomous Prefecture are major tourist destinations, but they sit in the heart of Yunnan province between major cities like Kunming and Dali. The improved connectivity is expected to promote tourism development and economic growth in central Yunnan, giving local agricultural products faster access to urban markets and reducing the isolation that has historically limited development in the region. Project manager told Chinese state media that the height difference between the bridge deck and the assembly yard is 320 meters high, or about 100 stories high. The complexity of this project is rarely seen in China. For a country that has built dozens of the world's highest and longest bridges, this is a significant statement. The single-tower design offers several advantages beyond just the engineering challenge it represents. In deep V-shaped valleys like the Lijiang Canyon, building towers on both sides can be prohibitively expensive because of the difficult terrain. A single-tower design reduces the amount of work needed on one side of the canyon, cutting construction costs and time while still achieving the necessary span. The bridge also had to withstand the region's environmental conditions. Yunnan province experiences significant temperature variations between seasons, strong winds funneling through mountain valleys, and occasional seismic activity. The bridge was designed to handle all of these forces while maintaining enough flexibility to prevent damage from thermal expansion and contraction. After completion, the Lujiang Bridge quickly became recognized as an engineering marvel, attracting international attention despite its remote location. The bridge demonstrates that when conventional engineering solutions won't work, innovation can create entirely new approaches that become the foundation for future projects. The Lujiang Bridge represents the cutting edge of suspension bridge design, a structure that exists only because engineers were willing to challenge the assumption that you need towers on both sides. But remarkable as this 798-meter single-tower span is, it's only number 5 on our list. The next bridge on our countdown doesn't break records for height or innovative design. Instead, it shatters the concept of what a bridge even means by stretching so far that it becomes its own kind of landscape, a structure so long that trains traveling across it at 300 kilometers per hour still need more than half an hour to complete the crossing. China is running out of water where it needs it most. The country's north and west are dry, the south and east have plenty. The solution: drill tunnels through mountain ranges and move the water. The Yinjiang-Buhan Water Tunnel is one of the most ambitious pieces of this strategy, and it's a project that sounds more like science fiction than civil engineering. Here's the problem. Yunnan province in southwest China has abundant water resources from rivers flowing off the Tibetan Plateau, but much of that water flows south into Myanmar, Laos, and Vietnam. Meanwhile, central Yunnan, where the provincial capital Kunming is located, suffers from chronic water shortages. The region has over 30 million people and extensive agriculture, but rainfall is seasonal and unreliable. China's solution is to divert water from the Jinsha River, the same river that flows through the Baihetan Dam, eastward into the dry central regions of Yunnan. But there's a massive obstacle: mountains. The river is on one side of a major mountain range, and the areas that need water are on the other side, so they're drilling straight through. The Yinjiang-Buhan Tunnel is part of this system, and it's mind-boggling in scale. The tunnel is 38.5 kilometers long and over 9 meters in diameter, large enough to drive a 2-story bus through. It's one of the longest water tunnels in the world, carved through solid rock at depths of up to 700 meters below the surface. Drilling a tunnel this size through a mountain isn't like digging a hole in your backyard. The rock is under enormous pressure from the weight of the mountain above it. When you drill through, that pressure is released and the rock wants to collapse inward. Engineers have to constantly reinforce the tunnel with steel supports and concrete linings as they go. The geology makes it even harder. The rock isn't uniform. It varies from hard granite to fractured zones filled with groundwater. Hit a water-bearing fracture and suddenly you have thousands of gallons per minute flooding into your tunnel. You have to pump it out while continuing to drill forward. Then there's the methane. Some of the rock formations contain pockets of methane gas under pressure. Break into one of those pockets and you risk explosions or poisoning the workers. Every meter of advance requires careful surveying to detect gas pockets before you hit them. The tunnel has to maintain a precise gradient, a gentle slope, to allow water to flow by gravity from the higher elevation of the Jinsha River to the lower elevation of central Yunnan. Get the gradient wrong, and water either flows too slowly or too fast, causing erosion or sediment buildup. Ventilation is a life or death issue. Workers are drilling kilometers underground with limited air circulation. The tunnel needs extensive ventilation shafts drilled down from the surface, with fans pushing fresh air in and pulling stale air out. But drilling ventilation shafts through hundreds of meters of rock is its own engineering challenge. Construction began in the mid-2000s and is expected to continue through the mid-2000s. At peak construction, tunnel boring machines, TBMs, worked from multiple access points simultaneously, boring toward each other with millimeter precision. When the different sections meet, they have to align perfectly, or the tunnel won't function properly. The payoff is enormous. When complete, the tunnel will help divert billions of cubic meters of water annually from the Jinsha River to central Yunnan. That water will supply drinking water to cities, irrigate farmland, and support industrial development in a region that's been chronically water-stressed. But it's not without controversy. Downstream communities that depend on the Jinsha River worry about reduced water flow. Environmental groups point out that diverting water changes ecosystem species adapted to certain river flows now have to adapt to less water. And there's the international dimension. The Jinsha River eventually becomes the Mekong, which flows through Southeast Asia. Any water diverted in China is water that doesn't reach countries downstream. China's response is that the diversion is a small percentage of the river's total flow and won't significantly impact downstream users. But when you're moving billions of cubic meters, even a small percentage is a lot of water. The Yinjiang-Buhan Tunnel is part of the larger Central Yunnan Water Diversion Project, which includes multiple tunnels, pipelines, and pumping stations. It's a massive, interconnected system designed to move water from where it's plentiful to where it's needed. And speaking of moving water on a massive scale, that brings us to number 2 on our list, a project that dwarfs even this ambitious tunnel. In the heart of Shanghai's bustling Pudong district, a towering trapezoid rises above the city like a vertical gateway to the future. The Shanghai World Financial Center, standing at nearly 500 meters, is not just a skyscraper. It is a statement of China's economic ambition and engineering daring. From the very first design sketches to the moment it topped out, this building's journey tells a story of patience, innovation, and overcoming seemingly impossible challenges. The idea for the tower was conceived in the late 1990s, at a time when Shanghai was transforming from a regional port city into a global financial hub. The government envisioned a vertical symbol that could represent the city's modern identity, a tower that would rival the world's tallest structures while fitting within the soft, reclaimed soils of the Huangpu River Delta. The initial concept was bold, a super tall with a circular opening at the top, designed to lighten the visual mass and reduce wind stress. However, cultural and technical considerations soon altered the design. By the early 2000s, the opening had been reimagined as a trapezoid, giving the building its distinctive bottle opener silhouette, a shape that is instantly recognizable across the skyline and a marvel of structural engineering. Construction officially began in 1997. Progress was immediately interrupted by the Asian financial crisis. Funding stalled, and for several years, the site lay partially excavated, a reminder of the economic uncertainty sweeping the region. Work resumed in 2003, but restarting the project was no simple task. Engineers had to reassess the design to meet updated safety standards, seismic codes, and new wind load calculations. Foundation, already partially in place, had to be carefully integrated with revised engineering plans to ensure that the tower could bear its colossal weight without settling unevenly in the soft delta soil. Building on Shanghai's soft, waterlogged ground presented one of the greatest challenges. To anchor the structure, engineers drove over 1,000 reinforced concrete piles deep into the bedrock, creating a foundation that could support the enormous mass of the skyscraper above. The tower's weight is astonishing. Nearly 1 million tons of concrete and steel hold up this vertical city. But it was not just about size, it was about balance. The engineers designed a central reinforced concrete core surrounded by a perimeter megaframe of steel. This combination allowed the structure to resist wind forces that can reach hurricane speeds at the upper floors while minimizing sway that could unsettle occupants. As the tower climbed, the construction story became one of precision and patience. At nearly 500 meters, wind loads increased dramatically, and every beam, floor slab, and elevator shaft had to be installed with meticulous care. Cranes lifted prefabricated components hundreds of meters above the ground, operating near their mechanical limits. Concrete for upper floors had to be pumped under extreme pressure, and workers contended with temperature fluctuations, humidity, and the risk of wind gusts strong enough to halt operations. Unlike smaller buildings, speed was never the main goal. Safety and alignment took precedence, and progress was often measured in meters per week rather than floors. By 2007, the Shanghai World Financial Center had begun to dominate the skyline. Its trapezoid opening, 100 meters across, created a dramatic visual contrast with the surrounding towers and reduced wind vortex effects that could otherwise twist the structure. But the project still faced delays. The elevator systems alone required complex engineering. Double-deck elevators capable of reaching the observation decks in less than a minute, with emergency systems designed to function in high winds and seismic events. Installing these systems took months of careful calibration and testing. Finally, the building topped out in 2008, over a decade after the initial groundbreaking. Fit-out and mechanical systems were completed the following year, and the tower officially opened in 2008. The cost was substantial, exceeding $1 billion, reflecting not just materials and labor, but also the sophisticated technology, deep foundation, and high-precision equipment required to bring it to life. What makes the Shanghai World Financial Center truly remarkable is not just its height, but the way it redefined the possibilities of urban construction. With 101 floors above ground and 3 below, the tower houses offices, hotels, observation decks, and mechanical floors in a vertical city that stretches nearly half a kilometer into the sky. For perspective, the building is taller than the Empire State Building, yet it feels lighter, more elegant thanks to the tapering form and the trapezoid aperture. Visitors stepping onto the observation deck experience a view that seems to float above the clouds, a dramatic testament to human engineering and ambition. The tower's story is also about resilience and adaptability. From design revisions caused by cultural considerations to the pauses enforced by economic crises, each challenge required innovative solutions. Every aspect of the project, from the megaframe structural system to the high-speed elevator installation, demonstrates a careful blend of ambition, technology, and problem-solving. China's engineers and planners proved they could build at a scale and speed unmatched in many Western cities, yet with a precision and sophistication that ensured safety and longevity. Today, the Shanghai World Financial Center is a landmark, not only for Shanghai, but for the world. It represents a period in China when the country was asserting itself on the global stage, using engineering and architecture as symbols of economic power. Every floor, every window, and every structural element tells a story of a city determined to rise, literally and metaphorically, above the challenges of finance, soil, wind, and time. From a bridge suspended from a single tower over a mountain valley, we now travel to the fertile lowlands of Jiangsu Province, where engineers have built something that redefines the very concept of a bridge. The Danyang-Kunshan Grand Bridge isn't just the longest bridge in the world, it's the longest structure of any kind ever built by humans, stretching an almost incomprehensible 164.8 kilometers. To put this in perspective, that's longer than the distance from Modena to Milan in Italy. It's longer than the width of many small countries. If you place this bridge in the United States, it would stretch from downtown Philadelphia well past Trenton, New Jersey, and the entire structure is elevated 30 meters above the ground, carrying high-speed trains at 300 kilometers per hour. The Danyang-Kunshan Grand Bridge opened in June 2011 as part of the Beijing-Shanghai High-Speed Railway, one of the most important transportation corridors in China. It connects Shanghai, the largest city in China with a population exceeding 24 million, to Nanjing, the capital of Jiangsu Province. The bridge runs through several major urban areas, including Danyang, Changzhou, Wuxi, Suzhou, and Kunshan, cities that are home to tens of millions of people combined. Construction began in 2006 and was completed in just 4 years, an astonishing timeline given the scale. The project employed 10,000 workers simultaneously at various points along the route, working in coordinated teams to build what amounts to a continuous viaduct nearly 165 kilometers long. The total cost was $8.5 billion, which breaks down to approximately $51 million per kilometer. The bridge consists of approximately 2,000 individual spans, each around 80 meters long. The structure is built as a viaduct, a segmented bridge made of smaller sections held up by piers and arches. About 9,500 concrete piers support the entire length, with 450,000 tons of steel used in the construction of the deck and support structures. Why build such an enormous elevated structure instead of laying tracks on the ground? The answer involves economics, geography, and practicality. Building a conventional railway line through this region would have required approximately 70 acres of land that would need to be acquired from farms, towns, and cities along the route. The elevated viaduct requires only 27 acres per kilometer, saving enormous amounts of valuable land in one of China's most densely populated regions. The terrain itself posed significant challenges. The Yangtze River Delta region is characterized by soft soil, wetlands, rice paddies, rivers, canals, and lakes. These conditions make building conventional foundations extremely difficult. An elevated viaduct solves these problems by lifting the entire railway above the problematic terrain, with piers driven deep into bedrock beneath the soft surface layers. The bridge also crosses approximately 150 river channels and waterways along its route. A 9-kilometer section spans the open waters of Yangcheng Lake in Suzhou, with 200 piers built in the lake to support this portion. For most of its length, the bridge follows parallel to the Yangtze River at distances varying between 8 and 80 kilometers to the south. The design incorporates both cable-stayed sections for longer spans and simple beam sections for shorter distances. This hybrid approach allows engineers to adapt the structure to different terrain and obstacles along the route without maintaining a single consistent design for the entire 165 kilometers. The flexibility of the design was key to completing such an ambitious project on schedule. Building a structure this long required accounting for Earth's curvature, over 164.8 kilometers. The curvature of the planet causes a measurable deviation from a perfectly straight line. Engineers used geodetic surveys and Earth radius calculations to adjust the elevation and alignment of different sections, ensuring trains could travel smoothly without encountering sudden grade changes or alignment issues. This level of precision over such distances represents a remarkable achievement in surveying and construction control. The bridge is designed to withstand magnitude 8 earthquakes, typhoons with sustained winds over 100 kilometers per hour, and impacts from naval vessels up to 300,000 tons, roughly equivalent to the largest cargo ships in the world. Each pier is equipped with elastomeric bearings and sliding plates that can absorb seismic shocks and allow the structure to flex during earthquakes without sustaining damage. Temperature presents another challenge for a structure this long. Steel and concrete expand when heated and contract when cooled. Over 164.8 kilometers, even modest temperature changes can cause expansion and contraction of several meters. The bridge design incorporates expansion joints at regular intervals that allow sections to move independently, preventing stress buildup that could damage the structure. The maximum clearance beneath the bridge is 150 meters in some sections, high enough for large cargo ships to pass beneath when the bridge crosses major navigation channels. Most of the bridge maintains an average height of 30 meters above ground level, high enough to cross local roads, railways, and waterways without interfering with ground-level traffic. The impact of the Danyang-Kunshan Bridge on regional transportation has been transformative. Before its construction, the journey from Beijing to Shanghai took 18 hours by conventional train. The high-speed railway, including this bridge as its longest continuous section, reduced that journey to less than 5 hours. Similarly, the trip from Ningbo to Jiaxing, which previously took 4.5 hours because of the need to navigate around lakes and rivers, now takes just 2 hours. This time, savings translates directly into economic benefits. Business travelers can make same-day trips between cities that once required overnight stays. Agricultural products from the fertile Yangtze Delta can reach markets faster. The industrial cities along the route have better access to labor pools and supply chains. The bridge has become a critical artery in one of the world's most economically productive regions. The construction process involved prefabricating most bridge segments in factories along the route, then transporting them to the installation site and lifting them into place with specialized equipment. This approach reduced disruption to the communities below and allowed for better quality control than would be possible with entirely on-site construction. Each prefabricated segment was precisely manufactured to match the calculated dimensions for its specific location along the bridge. During construction, engineers paid careful attention to environmental impacts. The bridge crosses sensitive lake ecosystems and agricultural land. Pier placements were adjusted to minimize disruption to aquatic life and soil displacement. The elevated design prevents the railway from fragmenting habitats and allows wildlife to move freely beneath the structure. The Danyang-Kunshan Bridge holds the Guinness World Record for the longest bridge in the world, a title it has held since opening in 2011. Remarkably, the same Beijing-Shanghai high-speed railway includes 2 other bridges in the top 10 longest bridges in the world: the Langfang-Qingxian Viaduct at 114 kilometers and the Tianjin Bridge at 113 kilometers. This concentration of extremely long bridges on a single railway line demonstrates China's commitment to infrastructure development in the 2000s and 2010s. The country transformed its construction capabilities to the point where building 100-kilometer-long elevated railways became routine rather than exceptional. Passengers traveling on trains crossing the Danyang-Kunshan Bridge don't see a dramatic landscape of soaring heights or deep valleys. Instead, they see rice paddies, rivers, lakes, and urban areas passing beneath at high speed. The bridge is so long that most passengers crossing it don't even realize they're on a single continuous structure. It simply becomes part of the landscape of the journey from Shanghai to Nanjing. The bridge requires continuous maintenance to keep it in service. Inspection crews regularly check every pier, every segment, every joint for signs of wear or damage. The sheer length of the structure means maintenance is a never-ending process. By the time crews finish inspecting one end, it's time to start again at the other end. This proactive maintenance ensures the bridge continues to perform safely despite carrying thousands of high-speed trains every week. At 164.8 kilometers long, the Danyang-Kunshan Bridge represents the ultimate expression of the viaduct concept, a structure so extensive it becomes its own geographic feature. If you thought one giant tunnel through a mountain was impressive, try imagining an entire network of tunnels, pipelines, reservoirs, and pumping stations designed to move water across an area the size of Germany. That's the Central Yunnan Water Diversion Project, and it's already under construction. The basic problem is simple but severe. Yunnan province has water in the wrong places. The western and southern parts of the province have abundant rainfall and river flow. The central and eastern parts, where most of the population and agriculture are concentrated, are dry. Kunming, the provincial capital with a metro population of over 6 million people, faces chronic water shortages. Historically, people adapted by using water sparingly and relying on limited local sources. But as the population grew and the economy developed, that strategy stopped working. Droughts became crises. Lakes and reservoirs dried up, agriculture suffered. Something had to change. The solution is to move water lots of it from the Jinsha River in the west to the dry central regions. The scale is staggering. The project aims to divert 3.4 billion cubic meters of water annually. That's enough to fill over 1.3 million Olympic swimming pools every year. But this isn't just about drilling one tunnel. The Central Yunnan Water Diversion Project is a complex, multi-phase system that includes over 660 kilometers of tunnels, including the Yinjiang-Buhan Tunnel we just discussed, hundreds of kilometers of pipelines and aqueducts, multiple pumping stations to lift water over mountain ridges, reservoirs to store water for dry seasons, treatment plants to ensure water quality, distribution networks to deliver water to cities and farms. The route crosses some of the most geologically complex terrain in China. The region sits on the edge of the Tibetan Plateau, with mountain ranges, deep valleys, and active fault lines. Tunneling through this landscape requires dealing with fractured rock, underground rivers, methane pockets, and high-pressure groundwater. In some sections, the tunnel is over 700 meters below the surface. That's deeper than 2 Empire State Buildings stacked on top of each other. At those depths, rock temperatures can exceed 30 degrees Celsius, making working conditions brutal for construction crews. The project also includes massive pumping stations that lift water hundreds of meters upward. Water is heavy. 1 cubic meter weighs 1 metric ton. Pumping billions of cubic meters of water uphill requires enormous amounts of energy. The project's pumping stations are some of the largest in the world, each with multiple high-capacity pumps powered by dedicated electrical substations. Water quality is another major concern. The Jinsha River water has to be treated before it's distributed to cities. The project includes multiple treatment plants that filter sediment, remove pollutants, and ensure the water meets drinking water standards. Construction began in 2016 and is being carried out in phases. Phase 1 focused on tunnels and basic infrastructure. Phase 2, currently underway, is expanding distribution networks and building additional storage capacity. Full completion isn't expected until sometime in the late 2020s. The cost is massive. Estimates range from $6 billion to $10 billion, depending on how you account for various components. That might sound like a lot, but consider the alternative. Without this project, Central Yunnan faces ongoing water crises that limit economic development and threaten quality of life for tens of millions of people. The benefits are already becoming apparent in areas where the project is operational. Cities that once rationed water during dry seasons now have reliable supplies. Farmland that was borderline viable is becoming productive. New industries that require significant water inputs are locating in the region. But critics raise important concerns. Diverting water from the Jinsha River affects ecosystems downstream. Fish populations change. Riparian habitats dry up. And there's the international aspect. The Jinsha becomes the Mekong, which flows through 6 countries. Water diverted in China is water that doesn't reach Myanmar, Laos, Thailand, Cambodia, and Vietnam. China maintains that the diversion represents a small fraction of the river's flow and includes agreements to maintain minimum downstream flows. But trust is in short supply when it comes to shared water resources. Domestically, there's concern about what happens if climate change alters rainfall patterns. The project assumes historical water availability in the Jinsha River. If droughts become more common, the amount of water available for diversion could decrease, making the entire investment less valuable. There are also questions about water rights and pricing. Who pays for this water? Should agricultural users pay the same as cities? What happens when demand exceeds the system's capacity to supply water? These are complex policy questions with no easy answers, but the physical project is moving forward regardless. Tunnels are being drilled, pipelines are being laid, pumping stations are coming online. The Central Yunnan Water Diversion Project represents China's confidence that engineering can solve resource scarcity problems. Whether that confidence is justified depends on factors, environmental, economic, and political, that will play out over the coming decades. But even this massive project, moving billions of cubic meters of water across an entire province, is only number 2 on our list. Because the number 1 megaproject is something that defies belief, a project so large that it makes central Yunnan look like a local irrigation ditch. In Hong Kong, land is a luxury, and the sky is the only frontier left. Rising to approximately 480 meters, the International Commerce Center, or ICC, is the tallest building in the city, and a striking example of what happens when ambition meets constrained space. But its story is far more than just numbers and glass facades. It is a tale of meticulous engineering, daring logistics, and construction ingenuity in one of the most densely populated cities in the world. The ICC project began in the mid-2000s as part of the massive Union Square development atop Kowloon Station. Unlike most skyscrapers that start on empty lots, ICC was built directly over a busy transit hub. Trains, tunnels, and a web of utilities ran beneath the site. Every foundation pour, every steel column had to account for this complex underground network. It was a puzzle that could not tolerate mistakes. Early site preparation took months longer than anticipated, as engineers excavated and reinforced the subterranean infrastructure while ensuring that daily train operations above ground were not disrupted. The design challenge was immense. Hong Kong's territory is mostly reclaimed land, with soft soil that can settle unevenly under extreme weight. For a tower of nearly half a kilometer, this was a major concern. To address it, engineers employed over 1,600 high-capacity reinforced concrete piles, each driven deep into the bedrock. The foundation alone required precision surveying and constant monitoring for settlement, because even a few centimeters of uneven movement could create catastrophic stress at higher floors. The foundation phase extended through 2007, marking the first significant milestone in what would become a decade-long journey. Once the base was completed, vertical construction began in earnest. The ICC's structural system is a hybrid, combining a central concrete core with perimeter steel columns that taper subtly toward the top. This combination gave the building both strength and flexibility, essential for resisting the strong typhoon winds that sweep Hong Kong each year. The tapering form wasn't just aesthetic, it helped reduce vortex shedding, a phenomenon where wind can cause a tall structure to twist or sway dangerously. Climbing nearly 100 floors above ground, the ICC's construction was a feat of vertical logistics. Cranes had to lift prefabricated components hundreds of meters, often stopping during high winds or heavy rain. Materials were delivered in a precise sequence to prevent congestion and delays. Every floor added complexity because the elevators, mechanical systems, and hotel and office spaces all had to be installed simultaneously in a vertical timeline. Construction crews worked around the clock, often in shifts of 12 hours or more, to keep pace with the ambitious schedule. Despite careful planning, the project faced several delays, excavation issues, typhoons, and the challenge of integrating the tower with surrounding infrastructure caused setbacks. In particular, the complexity of building over a live transit hub added weeks of careful coordination for every step. But these obstacles didn't slow the determination behind the project. By 2010, the ICC had reached its full height, a towering presence visible from across Victoria Harbour, dominating the Kowloon skyline and creating a new benchmark for urban super-tall construction. The ICC is not just a giant tower, it is a vertical city. It accommodates offices, a luxury hotel, observation decks, and mechanical floors, all stacked into one building. The observation deck, near the top, offers views that extend across Hong Kong and the South China Sea. From the harbor, the tower seems impossibly tall, nearly touching the clouds, a visual anchor for the city that is as much engineering marvel as aesthetic statement. For context, the ICC is taller than the iconic Empire State Building, yet it occupies far less horizontal space, a demonstration of vertical efficiency in one of the world's most densely populated urban areas. Financially, the tower was a massive undertaking. costs ran into the billions of US dollars, covering not only the materials and labor, but also the intricate engineering solutions required for its foundation and structure. It is one of the most expensive skyscrapers ever built in Hong Kong. Yet, the investment reflects more than construction. It symbolizes the city's determination to innovate and grow vertically despite geographic constraints. What makes ICC particularly remarkable is how it embodies China's, and specifically Hong Kong's, approach to skyscrapers, combining speed, precision, and audacity. Unlike earlier towers that unfolded slowly over decades, ICC's construction employed cutting-edge prefabrication, computer-aided simulations, and wind tunnel testing at every stage. Engineers could model how the building would sway in typhoons, how elevators would operate under full load, and even how temperatures at different heights would affect structural expansion. Every decision, from the type of steel used to the thickness of the glass panels, was calculated to balance safety, efficiency, and elegance. Today, ICC is more than a building. It is a marker of urban ingenuity. From the streets of Kowloon, it appears to rise effortlessly, but anyone who understands skyscraper engineering knows the story beneath. A decade of planning, an army of engineers and workers, a foundation hundreds of meters deep, and technology that lets a vertical city stand safely atop soft soil and a busy transit hub. It is a triumph of human design, a vertical expression of ambition in a city where horizontal space is a rare commodity. In the skyline of Hong Kong, the ICC stands as both icon and inspiration. In a region where land is scarce and the skies are busy, it demonstrates that the future belongs to those who can master both the ground below and the air above, just like the next tower on our list. The final three bridges on our list represent different engineering philosophies, each pushing boundaries in their own way. At number 3, we arrive at the Chiming Three Provinces Bridge, better known as the Jiming Bridge, which opened in January 2020 at one of the most remote and historically significant locations in southwestern China. The bridge spans the Qishui River at a point where three provinces, Sichuan, Yunnan, and Guizhou, meet. The location gets its name from a Chinese saying, "In the past, when a rooster crowed in the morning, the sound could be heard across all three provinces." But that proximity was deceptive. The steep canyon carved by the Qishui River meant that traveling from one side to the other required a journey of more than 2 hours through dangerous mountain roads and a ferry crossing. The Jiming Bridge reduces that journey to 2 minutes. The arch bridge stretches 286.4 meters across the canyon, with a main span of 180 meters and a height of 162 meters above the river. The structure is 11.5 meters wide, carrying 2 lanes of traffic plus sidewalks on both sides. What makes this bridge remarkable isn't just its technical specifications, it's the transformation it represents for one of China's most isolated regions. The area is home to 12 townships across 8 counties, places where poverty and isolation have been facts of life for generations. Before the bridge, farmers carrying baskets of plums from the Sichuan side to markets in Yunnan would begin their journey 2 days early. They'd walk down the mountain, cross the river by ferry, climb back up the mountain on the opposite side, sleeping on the roadside along the way. After reaching county markets, they could sell their plums for 0.5 yuan per kilogram, barely enough to cover the journey's costs. Construction took 3 years, from 2017 to 2020, and cost 59 million yuan, split equally between Shuyang County in Sichuan and Zhenxiang County in Yunnan. The project employed workers who lived on site in one of the most challenging construction environments in China. The bridge site was so remote that during winter, ice made the mountain roads impassable to trucks. Materials had to be transported during favorable weather and stockpiled for months. Workers crossing between the two construction sites didn't have the luxury of a bridge. They rode in a suspended cable car, welded from iron sheets and steel bars, rattling across the 310-meter span in about 20 minutes. The first person to ride this contraption, a clerk from Sichuan, called the foreman to make sure it was safe. He later joked that if the cage did fall, at least the drop wouldn't last long. The crane operators, a married couple named Zhang Chunhua and Chen Shijun, worked at the highest points of the construction site. 256 meters above the water. Zhang's husband taught her to operate the tower crane when she was 30. The first time she climbed up behind him, the structure shook and she was too frightened to move. By the end of construction, she faced that 256-meter drop every day and felt numb to it. The Qishui River itself holds historical significance. It's known as the River of Wines because several famous Chinese spirits, including Mao Tai, are produced along its banks. The river's distinctive reddish color comes from sediment concentration, giving it the name that translates to Red Water River. It was also the site of a major battle during Mao Zedong's Long March in 1935. The arch design was chosen for both aesthetic and practical reasons. Arch bridges can span longer distances than simple beam bridges while using less material than cable-stayed or suspension bridges. For this remote location where every ton of material had to be transported through treacherous mountain roads, efficiency mattered. The Yinjiang Bridge also serves as a gateway to tourist attractions. A cliff walk on the Sichuan side, more than 200 meters above the river, carved by villagers over 10 years using hand tools, is now accessible to visitors from all three provinces. What was once a desperate route to market has become a tourist destination, and the bridge makes it reachable. When the bridge opened to traffic on January 21, 2020, project manager Jiang Zhongqiao told reporters, "We spent 3 years building the bridge, and I am glad that it is finally open to traffic." For the approximately 12 townships and 8 counties in the region, the bridge represents more than infrastructure. It's an economic lifeline connecting communities that geography had separated for thousands of years. Yet, at 180 meters of span and 162 meters of height, the Yinjiang Bridge is modest compared to number 2, a bridge connecting not just provinces but entire regions, and transforming not just isolated communities, but some of the world's most economically important areas. What if you could take the water from your country's wet southern regions and move it thousands of kilometers north to the dry regions where hundreds of millions of people live? It sounds impossible. It sounds insane. China is doing it. The South-North Water Diversion Project is the largest water diversion project ever attempted in human history. Not just in China, in the world. Ever. Here's the problem China faced. The north has most of the people, most of the agriculture, and most of the industry, but it has very little water. The south has abundant water, but far fewer people. The Yellow River, which flows through the north, is overexploited and sometimes runs dry before reaching the sea. Beijing, a city of 21 million people, sits in a region with less water per capita than Saudi Arabia. For decades, China managed this imbalance through a combination of groundwater pumping, strict rationing, and limiting development. But groundwater levels were dropping, rationing was hampering economic growth, and the population kept growing. Something had to give. The solution, first proposed by Mao Zedong in the 1950s and finally implemented in the early 2000s, was to move water from the Yangtze River Basin in the south to the Yellow River Basin and northern cities. Not a little water massive amounts. The goal is to eventually transfer 44.8 billion cubic meters of water per year. To put that in perspective, that's enough water to supply the entire United Kingdom for nearly 2 years. Every year. The project consists of 3 massive routes: eastern, central, and western, each taking water from different points along the Yangtze and moving it north through different pathways. The eastern route starts near the Yangtze Delta and pumps water north through a series of canals, rivers, and lakes. It's over 1,150 kilometers long and includes multiple massive pumping stations because the route goes uphill. Water has to be lifted over 65 meters in elevation. Think of it as a staircase for water, where each step is a pumping station lifting millions of tons of water to the next level. This route became operational in 2013 and supplies water to cities in Jiangsu and Shandong provinces, eventually reaching as far north as Tianjin. The central route is even more ambitious. It starts at the Danyang-Kunshan Reservoir on the Han River, a Yangtze tributary, and flows north via a specially constructed canal system. The route is 1,432 kilometers long, roughly the distance from New York to Miami, and supplies water to Henan, Hebei, Beijing, and Tianjin. The beautiful thing about the central route is that it flows by gravity. The water starts at a higher elevation and flows downhill all the way to Beijing. No pumping required for the main canal, but that meant the canal had to be built with an incredibly precise gradient, dropping just 0.0001. That's 1/10,000th in slope. Get that wrong, and water either flows too fast, causing erosion, or too slow, causing sediment buildup. The canal also had to cross rivers, roads, and railways. In many places, they built aqueducts channels that carry water above ground level, spanning valleys and crossing highways. In other places, they built tunnels to pass under obstacles. The logistics of constructing over 1,400 kilometers of precisely graded canal, complete with crossings and control structures, is staggering. The central route became operational in 2014, and it's already delivering billions of cubic meters of water annually to northern China. Beijing now gets a significant portion of its water supply from this route, easing pressure on local groundwater. Then there's the western route. This one is still largely in the planning phase, and it's by far the most controversial and technically challenging. The western route would take water from the headwaters of the Yangtze River on the Tibetan Plateau and divert it into the headwaters of the Yellow River. The catch? This region is at elevations of 3,000 to 4,000 meters above sea level. The terrain is remote, mountainous, and seismically active. Building infrastructure here means working in conditions that challenge human endurance. The route would require multiple large tunnels through mountain ranges, dams to create reservoirs, and infrastructure capable of operating in freezing temperatures and high-altitude conditions. Estimated costs for the western route run into tens of billions of dollars, and completion, if it happens, wouldn't be until the 2030s or beyond. Critics of the western route point out the environmental impact. The Yangtze's headwaters are crucial to ecosystems throughout the river basin. Diverting water at the source could have cascading effects downstream. There are also concerns about impacts on the Tibetan Plateau's fragile environment. The entire South-North Water Diversion project has already cost over $80 billion, with the eastern and central routes operational and the western route still in planning. When complete, all three routes combined would transfer nearly 45 billion cubic meters of water annually. That's about the same as the annual flow of the entire Colorado River in the United States. The human impact of construction was enormous. Over 330,000 people were relocated to make way for reservoirs and canals. Ancient villages were flooded. Agricultural land was taken. The social disruption was significant, though the government provided compensation and resettlement housing. Environmentally, the impacts are complex. On one hand, the project eases pressure on northern groundwater aquifers, which were being depleted at unsustainable rates. On the other hand, diverting water from the Yangtze alters ecosystems along that river. Species adapted to certain water levels and flow rates now face changed conditions. There are also questions about water quality. Moving water through canals and pipelines risks contamination from agricultural runoff, industrial discharge, and urban pollution. The project includes extensive water treatment facilities, but maintaining water quality across thousands of kilometers is an ongoing challenge. Economically, the benefits are clear for northern China. Cities like Beijing no longer face the immediate prospect of running out of water. Agriculture in water-stressed provinces has more reliable irrigation. Industries that require significant water inputs can continue operating. But there's a cost beyond the construction budget. Water doesn't come free. Users pay for the water delivered by the project, and those costs are passed on to consumers and businesses. There are ongoing debates about pricing. Should water be subsidized to encourage economic development or priced at full cost to encourage conservation? These are complex policy questions with no easy answers. But the physical project is moving forward regardless. Tunnels are being drilled. Pipelines are being laid. Pumping stations are coming online. The South-North Water Diversion project is expected to be fully operational, including the western route, by sometime in the 2040s. When complete, it will have reshaped China's water geography, moving water on a scale that's never been attempted before. It's a testament to what modern engineering can achieve, and a reminder that solving resource scarcity problems at a national scale requires thinking big, really big. Changsha is not a coastal megacity. It is not a global financial hub. And that is exactly why this tower matters. At around 450 meters, Changsha IFS Tower T1 rose rapidly in the 2000s and 10s, surprising many observers. Construction began around 2013, during a period when China's interior cities were accelerating their development. The pace was relentless. Floor after floor climbed in quick succession, high-strength concrete, prefabricated components, and around-the-clock construction schedules made speed possible. Engineering focused on efficiency. The tower uses a reinforced concrete core with perimeter columns designed for both gravity and lateral loads. Simple, robust, scalable. By 2017, the tower was complete. In just a few years, Changsha had gained a skyline landmark that rivaled coastal giants. The cost ran into the hundreds of millions, but the real story is speed. This building showed how China could replicate super-tall construction far beyond its traditional centers. In the rapidly modernizing city of Changsha, far from the coastal hubs of Shanghai or Hong Kong, a new kind of skyline ambition took shape, rising to approximately 450 meters. The Changsha IFS Tower T1 is the tallest building in Hunan province, a vertical statement of technological mastery and urban transformation. Yet its story is less about glamour and more about the sheer audacity of building a super tall in a city not traditionally known for skyscrapers, demonstrating China's ability to spread its engineering prowess inland. Construction began around 2013, during a period when Chinese cities far from the eastern coast were embracing rapid urbanization. Changsha's leaders wanted a symbol of modernity, a tower that would redefine the city's skyline, attract investment, and signal that the city could compete with its more famous counterparts. The challenge was monumental: build a 450-meter super tall on a site that was already dense, with limited space for staging materials, cranes, and construction logistics. The first step was the foundation. Changsha's soil is a mix of clay and bedrock, which required extensive soil stabilization. Engineers installed hundreds of deep piles, reinforced with steel and high-strength concrete to anchor the tower safely into the ground. Advanced monitoring systems tracked settlement constantly, ensuring that even minor shifts were corrected immediately. Unlike more forgiving sites in coastal cities, here every centimeter mattered because there was little room for error. Once the foundation was complete, vertical construction began with astonishing speed. The tower rose floor by floor, leveraging prefabricated floor slabs and modular construction techniques to accelerate the schedule. The combination of concrete core and perimeter steel columns allowed each floor to be erected quickly without sacrificing stability. Workers often operated in shifts around the clock, keeping the project moving at a pace that was remarkable for a city just beginning to develop super-tall construction expertise. The design itself was a bold statement of modern engineering. The building tapers slightly as it rises, reducing wind load and ensuring stability. Engineers used outrigger trusses connecting the core to the perimeter columns, allowing the tower to flex safely in strong winds. The upper floors are equipped with dampers to absorb sway, a subtle but essential feature that keeps occupants comfortable while minimizing stress on the structure. The building is a technical marvel, yet the engineering is seamless, invisible to the casual observer who sees only a sleek vertical form dominating the Changsha skyline. Despite careful planning, the project encountered challenges. The rapid pace of construction sometimes conflicted with supply logistics. High-strength concrete had to be delivered on schedule and poured quickly, or floors could not be completed in time. Equipment failures, weather delays, and the occasional typhoon threatened to slow progress. But the construction team adapted, using prefabrication and precision scheduling to maintain momentum. By 2017, just 4 years after breaking ground, Changsha IFS Tower T1 had topped out, a testament to both efficiency and determination. The interior fit-out took another year, incorporating offices, retail spaces, and luxury apartments. At the very top, Observation decks and mechanical floors required meticulous attention because the stresses at the uppermost levels are far higher than at the base. Elevator systems designed to move thousands of people efficiently had to be calibrated for speed, weight, and safety. Even the glass curtain wall, which appears uniform and smooth, was engineered to resist wind pressures and thermal expansion across the building's height. From the ground, the tower's scale is almost dizzying. Standing next to older mid-rise buildings, it seems impossibly tall, stretching into the clouds. At 450 meters, it is taller than New York's Empire State Building, yet its footprint is comparatively modest, giving it a sense of vertical elegance. The tapering form, combined with reflective glass, creates the impression that the building is both light and strong, a visual illusion crafted through engineering precision. Financially, Changsha IFS Tower T1 represents a major investment in the city's future. Costs were estimated in the hundreds of millions of dollars, including foundation stabilization, high-strength materials, prefabrication technology, and specialized elevator systems. For a city of Changsha's size, this was a transformative commitment, signaling that urban growth and modern architecture were not limited to coastal megacities. Beyond the numbers, the tower has had a profound symbolic impact. It demonstrates that the super-tall skyscraper era in China is not confined to Shanghai, Beijing, or Shenzhen. Cities inland can now dream big, relying on advanced engineering, rapid construction techniques, and innovative logistics to realize projects that might have been unimaginable a decade earlier. The tower serves as both a literal and figurative beacon, reshaping the skyline while inspiring future development throughout the region. Changsha IFS Tower T1 also exemplifies China's methodical approach to skyscraper construction. Plan meticulously, innovate constantly, and build with speed and precision. From its deep foundation to its high-tech elevator systems, from wind-resistant design to prefabricated floors, every element was orchestrated to overcome both geographic and technical challenges. The result is a building that feels effortless in its majesty, yet every meter is the product of painstaking work and sophisticated engineering. Today, the tower dominates the Changsha skyline, visible for miles in every direction. For engineers, it is a case study in high-rise construction in emerging urban centers. While the Zifeng Bridge connects remote mountain communities, the Kong-Zhuhai-Macau Bridge connects three of the most economically dynamic cities in Asia. At 55 kilometers long, it's the longest sea crossing system in the world and one of the most complex engineering projects ever completed. The bridge opened in October 2018 after 9 years of construction, linking Hong Kong, Zhuhai, and Macau across the Pearl River estuary. Before this bridge, traveling by road from Hong Kong to the other two cities required a 4-hour journey around the estuary. The bridge reduces that to just 45 minutes, fundamentally reshaping the Pearl River Delta's economic geography. The structure isn't a single continuous bridge. It's an integrated system consisting of 3 cable-stayed bridges, a 6.7-kilometer undersea tunnel, and 4 artificial islands. This combination was necessary because the Pearl River estuary is one of the world's busiest shipping channels, and a bridge stretching the entire distance would obstruct navigation. The 3 cable-stayed bridges span the shallowest sections of the estuary, with their navigation clearances allowing ships to pass beneath. The longest of these, the Qingzhou Channel Bridge, has a main span of 458 meters and towers rising 163 meters above the water. These bridges alone would be considered major achievements, but they're just components of the larger system. The artificial islands serve as transition points where the bridge dives underwater. These islands, built using giant steel cylinders driven into the seabed and filled with sand, had to be constructed in water depths exceeding 40 meters with strong currents and frequent typhoons. Each island covers an area equivalent to several football fields and houses ventilation equipment for the tunnel sections. The 6.7-kilometer undersea tunnel consists of 33 immersed tube sections, each 180 meters long and weighing 80,000 tons. These were prefabricated on land, floated to the installation site, and sunk into a pre-dredged trench on the seabed. The precision required was extraordinary. If the sections didn't align within millimeters, water would leak into the tunnel. The tunnel section was necessary for a specific reason. Hong Kong International Airport sits directly above part of the crossing route. A bridge would interfere with aircraft flight paths, so engineers designed the tunnel to pass beneath the airport approach lanes, maintaining aviation safety while creating the crossing. Construction faced challenges unprecedented in bridge engineering. The Pearl River estuary experiences typhoons regularly, with waves that can exceed 10 meters in height. The structure had to withstand magnitude 8 earthquakes, ship collisions from vessels up to 300,000 tons, and temperature variations that cause expansion and contraction across the entire 55-kilometer length. The bridge cost approximately about $17 billion, making it one of the most expensive infrastructure projects in history. The investment reflects not just the technical challenges, but the strategic importance of connecting the Guangdong-Hong Kong-Macau Greater Bay Area, a region with a population exceeding 70 million and an economy larger than most countries. The structure carries 6 lanes of traffic, with a speed limit of 100 kilometers per hour. Since opening, it has dramatically increased the flow of people and goods between the 3 cities, enabling same-day business trips that were previously impossible, and integrating labor markets and supply chains across the region. The Hong Kong-Zhuhai-Macau Bridge represents a different kind of ambition than mountain-spanning suspension bridges or record-breaking arch bridges. Its infrastructure is an economic strategy, a physical manifestation of China's goal to develop the Pearl River Delta. At 55 kilometers and $17 billion, it's the longest and one of the most expensive sea crossings ever built. Our final bridge combines technical innovation with a different kind of record. It is the longest arch bridge in the world, pushing a 2,000-year-old design concept to its absolute limit. Standing at approximately 450 meters, the Zifeng Tower, also known as the Greenland Center, is the tallest building in Nanjing and one of the earliest inland supertalls in China. Construction began in the mid-2000s, when Nanjing was pushing to modernize its skyline while preserving its historical identity. The challenge was building high without overwhelming the city. The city's leaders envisioned a tower that would not only reshape the skyline, but also serve as a symbol of economic confidence. Unlike coastal megacities with decades of skyscraper experience, Nanjing presented unique challenges. The soil was a mix of clay and soft sediment, the urban fabric was dense, and the construction team needed to integrate modern systems in a city with historic constraints. The foundation work alone was a monumental undertaking. Engineers drove hundreds of deep piles into the ground, anchoring them into solid strata below the soft surface soil. Continuous monitoring systems measured settlement to fractions of a centimeter, ensuring that as the tower rose, it remained perfectly vertical. Any miscalculation could have led to catastrophic structural problems. The foundation phase stretched over more than a year, a slow and meticulous prelude to the tower's ascent. Vertical construction began with a focus on precision and speed. The Zifeng Tower's core is reinforced concrete, a choice that provides both stiffness and strength. Surrounding this core are perimeter columns that gradually taper toward the top, giving the tower both stability against wind and elegance in its form. Engineers incorporated outrigger trusses and belt trusses, distributing wind and seismic forces efficiently through the structure. For a building of this height, these measures were essential. Without them, the upper floors would sway dangerously during typhoons or minor earthquakes, which are not uncommon in Jiangsu province. The construction team relied heavily on prefabricated components and innovative construction sequencing to maintain speed. Floors were often pre-assembled off-site and lifted into position, reducing the time workers needed at extreme heights. Cranes operated near their maximum capacity, lifting steel beams and reinforced concrete sections hundreds of meters above the street. Every day, engineers monitored the structural alignment, adjusting tension in the trusses and verifying verticality to ensure the tower remained within millimeters of design specifications. At times, construction paused temporarily to recalibrate, a necessary step to prevent cumulative errors as the building rose higher into the skyline. By 2009, just 4 years after breaking ground, The tower had topped out, yet topping out is only the beginning. Interior systems, including high-speed elevators capable of whisking passengers to the top in under a minute, mechanical floors, and luxury office fit-outs required meticulous attention. Curtain walls were installed with precision, designed to resist wind pressures, reduce thermal expansion, and provide uninterrupted panoramic views of Nanjing and the Yangtze River. Engineers even accounted for microclimatic effects, such as temperature differentials at high altitude, which could affect both structure and glass integrity. The scale of the tower is breathtaking. With 89 floors above ground and 3 below, Zifeng Tower houses offices, retail spaces, and luxury hotel accommodations. From street level, the building appears impossibly tall, dwarfing surrounding mid-rise developments. Standing next to older Nanjing structures, it is easy to forget the years of planning, calculation, and coordination that allowed it to reach nearly half a kilometer into the sky. For context, it is taller than most historic landmarks in the city and exceeds the height of the Eiffel Tower, yet occupies far less ground area, a masterclass in vertical efficiency. Financially, Zifeng Tower represented a massive investment in the city's future. Total costs ran into the hundreds of millions of dollars, covering deep foundation work, high-strength materials, prefabrication technology, and complex elevator and mechanical systems. For Nanjing, the investment was transformative, signaling that the city was capable of executing projects at the same technological and financial scale as the coastal megacities. The tower's impact extends beyond its physical presence. It reshaped the skyline, altered real estate values, and set a precedent for super-tall development in inland cities. It demonstrated that sophisticated engineering, high-speed construction techniques, and advanced logistics could be applied outside of traditional skyscraper hubs. Zifeng Tower became a model for other inland projects, proving that height, speed, and modernity were not limited to Shanghai, Beijing, or Shenzhen. Today, Zifeng Tower dominates Nanjing's skyline. Its reflective glass catches the sunlight across the Yangtze River. Its tapered silhouette balances visual grace with structural necessity, and its sheer presence signals economic vitality. Visitors can ride high-speed elevators to observation decks that offer uninterrupted views stretching across the city, glimpsing the full scale of urban growth below. Zifeng Tower proved that China's skyscraper boom was not limited to a few cities. It was national, systematic, and only getting started. We end our journey where we began, in Guangxi Province in southern China, with a bridge that represents the pinnacle of one of humanity's oldest structural forms. The Longtan Bridge, which opened to traffic in 2023, became the world's longest arch bridge with a main span of 600 meters, a distance that engineers once thought impossible for this type of structure. Arch bridges are among the oldest designs in human history. The Romans built stone arches that still stand 2,000 years later. But arch design has a fundamental limitation. The longer you make the span, the more the compression forces multiply exponentially. At 600 meters, the Longtan Bridge faces forces that would crush traditional materials instantly. To overcome these physics-defying challenges, Chinese engineers used a basket arch design constructed from high-strength steel tubes filled with concrete. This hybrid approach provides the compressive strength of concrete with the flexibility of steel, creating a structure that can handle enormous forces while absorbing vibrations from traffic and wind. The bridge is located in Guangxi's mountainous terrain, where deep river valleys have historically isolated communities. The Longtan Bridge crosses the Longtan Reservoir at a location where the gap between mountains measures 600 meters. Building traditional foundations on both sides and connecting them with any design besides an arch would have cost far more and taken much longer. The construction process required extraordinary precision. Workers erected temporary support structures in the middle of the reservoir, 200 meters above the water, just to hold the arch segments during assembly. If the two halves of the arch meeting in the middle were misaligned by even a few centimeters, the entire structure would be compromised. Temperature was another challenge. Across 600 meters, even modest temperature changes cause the steel to expand or contract by several centimeters. Engineers timed the final connection for the exact moment when temperatures were optimal, ensuring perfect alignment. The bridge cost approximately 1.6 billion yuan and took 5 years to complete. For that investment, China achieved more than a world record. They proved that the 500-meter barrier for arch bridges could be broken, and that ancient structural principles could be pushed to new extremes with modern materials and techniques. For the approximately 160,000 people living in the surrounding counties, the bridge transforms geography that has shaped settlement patterns for millennia. Communities separated by hours of mountain roads are now minutes apart. Agricultural products reach markets before spoiling. Medical facilities become accessible to entire regions. But the Tianyi-Longtan Bridge represents something beyond local impact. At 600 meters, it demonstrates that even the most thoroughly understood engineering principles still have room for innovation. The Romans would recognize the arch design, but the scale and materials would seem like magic to them. Big. From railways climbing to the roof of the world, to dams that generate more power than entire countries consume, to tunnels that move rivers across provinces, China's infrastructure megaprojects are redefining what's possible in the 21st century. What do you think? Are these projects impressive feats of engineering, or does the cost outweigh the gains? Let us know in the comments below. Keep following Signum, where we bring you the most inane stories of the world's greatest megaprojects.